Somewhere in the universe, right now, a star is having the worst possible day. Not the kind of bad day that involves a flat tire, or a passive-aggressive email, or discovering that someone has used the last of the milk and put the empty carton back in the fridge. Something considerably more final than that. A star roughly 30 times the mass of our Sun, a star that has been burning with almost incomprehensible ferocity for the past 3 million years, has, in the last fraction of a second, run out of fuel. Its core, which has been holding the whole enterprise together through the sheer force of nuclear fusion, has simply stopped. And gravity, which has been waiting patiently for exactly this moment, has moved in. What happens next takes less than a second. The core collapses, a black hole forms, the outer layers of the star, suddenly unsupported, fall inward, and then, in a kind of violent cosmic rebound, explode outward with a force that makes every nuclear weapon ever built on Earth look like a damp match. 2 jets of energy punch through the dying star's outer layers and tear out into space at close to the speed of light, carrying more energy than our Sun will produce across its entire 10 billion year lifetime. All of this takes about as long as it takes to blink. The flash of gamma rays that erupts from those jets, a burst of the most energetic light the universe produces, races outward across the cosmos. For a few seconds, this single dying star outshines every other star in its galaxy combined. Then it fades. The galaxy goes quiet. The photons keep travelling. They travel for a very long time. Billions of years, in fact, across distances so vast that the concepts we normally use for measurement begin to feel slightly embarrassed by their own inadequacy. The photons don't notice. Photons are not, as far as we can tell, prone to existential unease. They simply travel at the speed of light. Through the expanding universe, past galaxies that didn't exist when they set out, past the place where our own solar system will eventually form, past the early Earth, past the long, patient unfolding of life on this planet, until, on a particular morning, in the early 21st century, they arrive at a satellite in low Earth orbit. An instrument twitches, a number changes, an alert fires automatically, broadcasting coordinates to telescopes around the world. And somewhere, an astronomer's phone goes off at 3 a.m. Hello, and welcome to the Sleepy Astronomer. I'm so glad you're here. If you're new to these late-night wanderings through the cosmos, welcome. This is a show about the universe, the deep, patient, occasionally alarming universe, told slowly and in the dark. For people who find that the biggest ideas make the best company when everything else has gone quiet. And if space isn't your only obsession, you might also find a home on the Sleepy Geographer, where the Earth itself becomes the mystery, or the Sleepy Investigator, where the mysteries are rather more human in origin but no less intriguing for that. Both are waiting for you. Both will take you somewhere worth going. If you've been here before, it's wonderful to have you back. There is, as always, a warm corner saved for you. If tonight's episode finds you curious, or if it helps you sleep, or ideally both, the kindest thing you can do is follow or subscribe, so you don't miss the next journey into the dark. A rating or a share costs nothing and means rather a lot to me. And if you'd like to support the show directly, a subscription unlocks early access to new episodes, usually a day or two before everyone else. The link is in the description. Tonight, we're going to spend a few hours with the most violent explosions in the universe, which I appreciate sounds like the wrong kind of bedtime story. But I promise you, by the end of this, the violence will feel very far away, and the wonder will feel very close. That's the thing about gamma-ray bursts. The more you understand them, the less frightening they become, and the more extraordinary. Here is the strange thing that started all of this. Gamma-ray bursts were not discovered by scientists who were looking for them. There was no research program, no funding proposal, no carefully designed experiment aimed at detecting the most energetic events the universe produces. They were found by accident in 1967 by satellites the United States had launched to listen for Soviet nuclear weapons tests. The Vela satellites were pointed at Earth, monitoring for the characteristic gamma-ray flash of a nuclear detonation. On the 2nd of July 1967, they caught something, a burst of gamma rays, intense, unmistakable, real. The scientists examined the signal carefully. The timing was wrong for a bomb. The signature was wrong for a bomb, and most strikingly, it hadn't come from Earth at all. It had come from somewhere out there in the sky. They classified the data, filed it away, and went back to looking for bombs. It would be another 6 years before the detections were declassified and published, by which point the satellites had recorded 16 of these events, each one brief, each one intense, each one coming from a completely different direction. By the time the wider astronomical community got to see the data, the mystery was already deep, and it would take another 30 years to begin to solve it. The most powerful explosions in the universe, discovered by instruments designed for something else entirely. The universe, it turns out, does not wait to be studied. It simply announces itself and leaves us to work out what we heard. Tonight, we're going to do exactly that. So, find your most comfortable position, let the quiet settle around you. The star has already collapsed. The jets are already firing. The photons are already on their way. Let's go and meet them. It is 1967, and the Cold War is at its particular kind of terrible. Not the spectacular, explosive terrible of an actual war, more the slow, expensive, nerve-shredding terrible of two superpowers watching each other very carefully across a very large ideological divide, each quietly convinced the other is about to do something catastrophic. Everyone is building weapons, everyone is testing weapons, and everyone officially has agreed not to test those weapons in the atmosphere, in space, or underwater, because the 1963 Partial Nuclear Test Ban Treaty said so, and both sides signed it, and both sides remain deeply suspicious that the other was cheating. Which is why the United States launched the Vela satellites. The Velas were not telescopes in any romantic sense. They were not instruments of curiosity, pointed at the cosmos with wonder and an open question. They were instruments of surveillance pointed outward from Earth with a specific, practical, thoroughly unglamorous brief. Catch the Soviets if they detonated a nuclear weapon in space. Each satellite carried detectors tuned to the gamma-ray signature of a nuclear explosion, a very particular kind of flash with a very particular profile that no natural phenomenon was expected to produce. This assumption would not survive contact with the universe. On the 2nd of July 1967, the Vela 4 satellite caught something. A burst of gamma rays. Intense, sharp, real. The instruments registered it clearly. The scientists at Los Alamos who received the data looked at it carefully, with the specific, focused attention of people whose job it is to determine whether the world is about to become significantly worse. They ran through the checklist. Was this consistent with a nuclear detonation? They compared the signal against what a weapon test was supposed to look like. It wasn't right. The shape of the signal was wrong. A nuclear explosion produces a characteristic double-humped gamma-ray signature, the so-called double-humped bang-meter signal, which is one of those technical terms that sounds like it was invented by someone who had stopped taking their work entirely seriously, but was in fact carefully chosen and entirely precise. This signal didn't have the right shape. The timing was wrong. The intensity profile was wrong. And most strangely of all, it hadn't come from anywhere near Earth. The scientists looked at the data, they looked at each other, they classified everything, filed it carefully and went back to watching for bombs, which was, given the circumstances, probably the correct institutional response. You don't issue a press release about an anomalous signal when you work in nuclear surveillance. You note it, you store it, and you wait to see if it happens again. It happened again. Over the following years, as more Vela satellites went up and the network became more sensitive, the detections accumulated. By 1973, the satellites had recorded 16 of these events. Each one was brief, lasting anywhere from a fraction of a second to a few minutes. Each one was intense. Each one arrived from a different direction in the sky, with no apparent pattern, no clustering, no obvious preference for any particular region of the cosmos. They didn't repeat from the same location. They didn't correlate with anything the astronomers already knew about. They simply appeared, blazed briefly, and vanished. In 1973, a group of scientists at Los Alamos, Ray Klebesadel, Ian Strong, and Roy Olson, published a paper in the Astrophysical Journal titled, "With Admirable Restraint, Observations of Gamma-ray Bursts of Cosmic Origin." The word cosmic was doing considerable work in that title. What they were saying, carefully and precisely, was, these things came from space, not from Earth, not from the Soviet Union, from somewhere out there. They had no idea where. They had no idea what was producing them. They had 16 data points and a great deal of uncertainty. What they had done, without quite meaning to, was discover one of the deepest mysteries in modern astrophysics. The astronomical community received the paper with a mixture of excitement and skepticism that greets any genuinely unexpected finding, which is to say, some people were riveted and some people were quietly certain there must be a mundane explanation, and everyone agreed that more data was needed. More data was always needed. This is less a specific response to gamma-ray bursts, and more a general feature of science, which tends to treat "we need more data" as both a conclusion and a coping mechanism. Before we go any further into the mystery, it's worth spending a moment with gamma rays themselves, because understanding what they are helps explain why these bursts were so difficult to study, and why it took so long to work out what was producing them. Gamma rays sit at the extreme end of the electromagnetic spectrum. You are familiar with visible light, the narrow band of wavelengths that human eyes evolved to detect, spanning from red through orange, yellow, green, blue, and violet. Beyond violet, at shorter and shorter wavelengths and correspondingly higher and higher energies, lies ultraviolet, then X-rays, and finally gamma rays. Gamma rays are electromagnetic radiation of the highest energy. Photons so energetic that passing through ordinary matter is less an obstacle than a mild suggestion. This creates a very specific problem for astronomers. The Earth's atmosphere, which is enormously useful for things like breathing and preventing the surface from being scorched by solar radiation, is completely opaque to gamma rays. Every gamma-ray photon that arrives from the cosmos is absorbed high in the atmosphere, long before it reaches any instrument on the ground. You simply cannot do gamma-ray astronomy from the surface of the Earth. You need to get your instruments above the atmosphere, which in 1967 meant satellites, and satellites capable of gamma-ray detection were, almost without exception, military assets built for nuclear surveillance rather than scientific curiosity. The universe had chosen to announce its most violent events in the one wavelength that required a space-based detector, at a moment in history when the only space-based detectors were classified. The timing was, depending on your perspective, either unfortunate or entirely typical of the universe's general attitude toward human convenience. And then there was the localization problem. Even setting aside the atmosphere, even granting yourself a perfectly functional gamma-ray detector in orbit, you still faced a fundamental practical difficulty. Gamma-ray instruments of that era could tell you that a burst had occurred, and roughly which region of the sky it had come from, but only roughly. The error boxes, the patches of sky within which the source might be located, were enormous. We are talking about regions covering many square degrees of sky. To put that in perspective, the full moon occupies about half a degree. An error box of several square degrees contains an almost uncountable number of stars and galaxies. Finding the specific source of a gamma ray burst within such a region was like being told that your lost keys were somewhere in the city, and the city was quite large, and also the keys had disappeared. By the time you'd worked out even that rough position, the burst was over. There was nothing left to point a telescope at. The sky in that direction looked exactly like every other patch of sky. Stars, galaxies, emptiness. No flashing arrow, no lingering glow, no convenient label reading, "It was this one." Gamma-ray bursts were ghosts. They arrived, they blazed, they vanished. And for the first decade after their discovery, astronomers could do little more than record their arrival times and marvel at how little the data was giving them to work with. But the data was giving them something, and by the late 1970s and 1980s, that something had crystallized into the question that would define the field for the next 20 years. Where were these things? Not in the philosophical sense, not what galaxy, what star, what cataclysm. In the most basic, practical sense, how far away? Because distance in astronomy changes everything. The same burst that looks moderately energetic from close by becomes almost physically impossible from far away. An event that seems plausible at the distance of, say, our own galaxy becomes something that strains the known limits of physics if it turns out to be billions of light-years distant. Distance was not an abstract question. It was the question on which everything else depended. And the astronomical community divided with genuine passion and entirely reasonable disagreement into two camps. In one corner, the galactic theorists. These were scientists who argued that gamma-ray bursts were relatively nearby, occurring within or just around our own Milky Way. The argument had a certain appealing logic. If the bursts were local, the energy required to produce them was manageable. Not comfortable, not easy to explain, but at least within the range of things physics could conceivably accommodate. Various proposals were put forward for what might be producing them. Comets falling onto neutron stars, starquakes on the surfaces of those same neutron stars, flares from unusual classes of nearby objects. Each hypothesis had its advocates and its problems. In the other corner, the cosmological theorists. These were scientists who looked at the distribution of bursts across the sky and saw something that troubled them deeply. If gamma-ray bursts were occurring within the Milky Way, they should show some preference for the galactic plane, the flat disk of the galaxy where most of the stars live. They should cluster, even slightly, toward the galactic center. Instead, the map of detections showed something unsettling in its evenness. The bursts were distributed across the sky with a uniformity that matched the distribution of distant galaxies far better than it matched anything local. The sky, as far as gamma-ray bursts were concerned, looked the same in every direction, and the only things that look the same in every direction when you're standing inside of the Milky Way are things that are so far away the galaxy's own structure becomes irrelevant. If the cosmological theorists were right, gamma-ray bursts were happening billions of light-years away, which meant the energy required to produce a flash detectable at that distance was not manageable. It was not comfortable. It was not within any obvious range of things physics could easily accommodate. It was, frankly, absurd, and yet the data kept pointing that way. The debate ran for the better part of 2 decades. Papers were published, conferences were held, arguments were made with the particular intensity of people who care deeply about being right and who have, in lieu of definitive evidence, only the quality of their reasoning to rely on. The field was, in the most honest possible sense, stuck. What it needed was a breakthrough. Not another theory, not another argument, not another carefully worded paper suggesting that one camp had slightly better logic than the other. It needed data. The kind of data that arrives not from argument, but from observation, from pointing an instrument at the right thing at the right moment, and seeing, clearly and unambiguously, what is actually there. That instrument was coming. In 1991, NASA launched the Compton Gamma Ray Observatory, carrying an instrument called BATSE, the Burst and Transient Source Experiment, that would detect gamma-ray bursts at a rate of roughly 1 per day, accumulating nearly 3,000 detections over 9 years. The map of those detections plotted across the whole sky would be one of the most important images in the history of astronomy. It showed something extraordinary in its ordinariness. No clustering, no galactic preference, no hint of structure, just dots scattered with almost eerie uniformity across the entire sky in every direction, as featureless and democratic as a handful of salt thrown against a black ceiling. The galactic theorists looked at this map and felt uneasy. The cosmological theorists looked at it and felt cautiously vindicated. But the map alone couldn't settle the debate. Uniformity of distribution was consistent with a cosmological origin, but not proof of one. The argument needed one more thing, a distance measurement, a single burst pinned down precisely enough that astronomers could point a proper telescope at the source and measure its redshift, the stretching of light wavelengths that reveals with mathematical certainty how far away something is. That measurement was also coming. It was just going to take a little longer and require a satellite launched by a collaboration of Italian and Dutch scientists, and involve more than a few sleepless nights in observatories around the world. But we are getting ahead of ourselves. The year is still 1967, at least in spirit. The Vela satellites are still watching. The data is still classified. Somewhere in the universe, stars are still dying in spectacular and unwitnessed fashion, their gamma-ray announcements racing across the cosmos toward instruments that don't yet exist, toward scientists who haven't yet been born, toward a mystery that won't be solved for another 30 years. The universe, as usual, is patient. It can wait. Imagine you are a detective and someone has just reported a crime. Not a cold case, a live one. It happened moments ago, somewhere in the city. Witnesses have confirmed that something occurred. The instruments agree, but the address is approximate. The neighbourhood is large, and by the time you arrive at the general vicinity, which took a while because traffic was terrible and the radio call was imprecise, there is no crime scene, no evidence, no lingering trace of anything unusual. Just streets and buildings and ordinary life, exactly as it would look if nothing had happened at all. The event was real. You simply cannot find it. This was gamma-ray burst astronomy for most of the 1970s, 1980s, and early 1990s. The bursts were real. No one seriously doubted that anymore. The instruments were detecting them reliably, at a rate of roughly one per day once BATSE was operational. But detecting a burst and studying a burst turned out to be two entirely different things, separated by a practical difficulty so fundamental it bordered on philosophical. The burst was always over before you could look at it properly. And this requires a little unpacking, because it is not immediately obvious why it should be so hard. The problem begins with how gamma-ray detectors work. A gamma-ray instrument doesn't form an image the way an optical telescope does. It doesn't have a lens that focuses light onto a sensor, producing a sharp picture of the sky with sources pinpointed at precise locations. Gamma rays are too energetic for that. They pass through most materials rather than being focused by them, which makes conventional optics useless and forces astronomers into more indirect approaches. Early gamma-ray detectors were essentially sophisticated counters. They could tell you how many gamma-ray photons were arriving, and from roughly which direction, but the roughly was doing an enormous amount of work. The result was the error box. When a burst was detected, the instruments could define a region of sky, a box of uncertainty, within which the source was probably located. In the early years, these boxes covered several square degrees of sky. To give that some context, the full moon occupies about a quarter of a square degree. An error box of several square degrees contains many thousands of stars and potentially hundreds of galaxies. Searching it for the source of a transient event that had already ended was not so much looking for a needle in a haystack as looking for the memory of a needle that had briefly been in a haystack and was now gone. And the clock was always running. Every second of delay between a burst being detected and a telescope being pointed at the right region was a second in which whatever had produced the burst was fading. Radio astronomers tried to catch lingering emission. X-ray observatories scanned the error boxes. Optical telescopes swept the regions in the hours and days after a detection, photographing everything and comparing the images against archival sky surveys, looking for something that had appeared and then, ideally, was still fading. They found almost nothing. For nearly 3 decades, every search came back essentially empty. The gamma-ray burst had been there, briefly and brilliantly, and then it had been gone. The sky kept its secret with an indifference that was, to the scientists spending their careers on this problem, increasingly maddening. The most important thing the field lacked was an afterglow. Theory suggested one should exist. When a gamma-ray burst fires its jets into the surrounding space, those jets don't simply switch off cleanly when the prompt gamma-ray emission ends. The jet material plows into the gas and dust of the surrounding environment, driving a shockwave outward, and that shockwave should glow, not in gamma-rays, but in X-rays, then ultraviolet, then visible light, then radio. The afterglow should brighten briefly, and then fade over hours, days, weeks, long enough in principle for a telescope to find it and study it, provided the telescope was pointed at the right place quickly enough. The catch, of course, was that the right place required a precise position, and a precise position required a detector capable of localizing the burst to a region small enough that a follow-up telescope could actually search it. The error boxes of the early detectors were simply too large. By the time an optical telescope had swept even a fraction of the region, any afterglow that existed would have faded beyond detection. What was needed was a satellite that could not only detect the burst in gamma rays, but rapidly pivot to examine the same region in X-rays, a more focusable wavelength, and pin down the position to an area small enough for ground-based telescopes to search in the hours immediately after the detection. This was a technically demanding requirement. It was also, as the 1990s progressed, becoming increasingly achievable. The interplanetary network deserves a mention here because it represented the field's most ingenious workaround in the years before a better solution arrived. The principle is simple and rather elegant. If a gamma-ray burst is detected by two spacecraft in different parts of the solar system, it will arrive at each spacecraft at a slightly different time. Because the two craft are at different distances from the source, the difference in arrival time, measured precisely, tells you something about the direction the burst came from. With three or more widely separated spacecraft, you can triangulate a position considerably more precisely than any single instrument could manage alone. The interplanetary network, a loose, informal collaboration of spacecraft that had been built for other purposes but happened to carry gamma-ray detectors, did exactly this throughout the 1980s and 1990s. Mars probes, Venus probes, spacecraft drifting through the outer solar system on unrelated missions. All of them quietly contributed their detection times to a global effort to pin down the positions of gamma-ray bursts more precisely. It was collaborative science of a pleasingly improvised kind, assembling a tool from spare parts that no one had originally intended to work together. The positions it produced were better, sometimes considerably better, than what a single satellite could achieve, but they still couldn't be turned around quickly enough or made precise enough to catch an afterglow in time. The network was a step forward, it was not the breakthrough. The breakthrough, when it came, wore Italian and Dutch flags. Beppo Sachs was a collaboration between the Italian Space Agency and the Netherlands Agency for Aerospace Programs, launched in April 1996. It was not the largest satellite, or the most powerful, or the most celebrated before it launched. It was, however, equipped with something that would prove transformative, a set of X-ray cameras with a field of view wide enough to catch a burst and narrow enough to localize it to a region a few arc minutes across, roughly equivalent to the apparent size of the Moon, rather than the many-degree error boxes of previous detectors. And crucially, Beppo Sachs could be commanded to rotate and point its narrow-field X-ray cameras at a burst position within a few hours of detection. A few hours sounds like a long time. It was, by the standards of what had come before, revolutionary. On the 28th of February 1997, Beppo Sachs detected a gamma-ray burst. The instruments recorded it, the team calculated the approximate position, and the satellite was rotated to examine the region with its X-ray cameras. What they found, an X-ray source fading in a location consistent with the burst, was the first confirmed X-ray afterglow of a gamma-ray burst. The position was narrow enough to be searched optically. Telescopes were alerted. Within hours, an optical counterpart was identified, a fading source of visible light at a precise location in the sky. For the first time in 30 years of trying, astronomers had something to point a telescope at, and they pointed every telescope they could. What those telescopes found in the spectrum of the fading optical afterglow was the answer to the question that had consumed the field for 2 decades. Redshift. The host galaxy of the burst, the galaxy from which the event had originated, showed a redshift corresponding to a distance of about 6 billion light-years. Not within the Milky Way, not in any nearby galaxy, not in our galactic neighbourhood in any sense that the word neighbourhood could stretch to accommodate. 6 billion light-years. The light from this event had been travelling since before the Sun existed. The debate was over. Gamma-ray bursts were cosmological. They happened at the far edge of the observable universe, and they were bright enough to be detected from there. The galactic theorists, who had spent years arguing for a local origin, absorbed this result, with the particular quiet of scientists who know when the evidence has moved decisively against them. The cosmological theorists, who had been saying this for years, absorbed it with the particular quiet of scientists who have learned that being right doesn't always feel as satisfying as expected, when the alternative would have been so much more convenient. Because the implications of a cosmological distance were, to put it gently, staggering. If a gamma-ray burst was detectable from 6 billion light-years away, if those photons had spread out across half the observable universe and still arrived at Earth with enough intensity to trigger the detectors, then the total energy released at the source must have been almost incomprehensibly large. The numbers, when the astronomers ran them, came out bigger than anything previously observed. More energy released in a few seconds than the Sun will produce in its entire lifetime. More energy than most astrophysicists had been willing to even hypothesize. The universe, it turned out, was capable of something that made the most extreme objects previously known look understated. How it was doing this would take a little longer to understand, but the where was now settled, and the where turned out to be almost as astonishing as the what. With the distance question resolved, the data that had been accumulating for decades could be read in a new light, sometimes literally. Astronomers began systematic campaigns to catch afterglows as rapidly as possible, building on Beppo Sachs's approach and pushing for ever faster response times. Each afterglow that was caught added a new data point, another distance, another host galaxy, another set of measurements that could be compared against the growing theoretical models of what these events actually were. And as the data accumulated, a pattern began to emerge that nobody had quite anticipated. Gamma-ray bursts were not a single phenomenon, they were two. The clearest division appeared in the duration of the bursts themselves. Some bursts lasted more than 2 seconds, often much more, with some stretching to minutes. Others lasted less than 2 seconds, sometimes only a fraction of a second, with a sharpness and brevity that seemed qualitatively different from their longer cousins. When astronomers mapped these two populations against their host environments, the distinction deepened. The long bursts seemed to prefer young, actively star-forming galaxies, places where massive stars were being born and dying at a high rate. The short bursts appeared in older stellar environments, places where the frantic business of star formation had slowed or stopped long ago. Two populations, two environments, almost certainly two different physical origins. The long bursts, with their preference for star-forming regions, pointed towards something involving the deaths of massive young stars. That story would come together quickly, and we'll get to it shortly. The short bursts were more mysterious. Their brevity and their old stellar environment suggested something that had been quietly waiting for a very long time before producing its explosion. What was sitting in those old, quiet galaxies, patient across billions of years, waiting for exactly the right moment? The answer to that question would take another decade to confirm, and it would require a completely new way of listening to the universe, one that didn't use light at all. But that is still ahead of us. For now, the field has crossed its first great threshold. Gamma-ray bursts are real. They are cosmological. They are the most energetic events ever observed. And for the first time, astronomers have the tools to study them properly, to catch their fading afterglows, to measure their distances, to begin to ask not just where they are, but what, precisely, is producing them. The ghost signals have been traced to their source. Now the real investigation begins. There is a number at the heart of this chapter, and it is going to be uncomfortable. Not uncomfortable in the way that some numbers are uncomfortable, the ones involving tax returns, or the age you feel when you try to get up off the floor too quickly. Uncomfortable in a deeper, more structural way. The kind of uncomfortable that comes from asking a perfectly reasonable question, doing the arithmetic carefully, checking it twice, and arriving at an answer that the known laws of physics look at with profound skepticism. The question is simple enough. We know how bright a gamma-ray burst appears when it arrives at our detectors. We know how far away it is, 6 billion light-years, in the case of the first burst whose distance was measured, and comparable distances for hundreds of bursts detected since. If you know how bright something appears and how far away it is, you can calculate how much energy it must have released at the source. The mathematics is the same mathematics you'd use to work out how powerful a light bulb must be if you know how bright it looks from 100 meters away. So astronomers did the calculation, and the answer came back: more energy released in a few seconds than our sun will produce across its entire 10 billion year lifetime. They checked it again. The answer was the same. They checked their assumptions, reviewed their data, looked for sources of error. The answer remained what it was. The universe, consulted on this matter, declined to apologize. To sit with this number properly, it helps to have some sense of what the sun actually produces. Our sun is not, by stellar standards, an especially impressive object. It is a perfectly competent, middle-aged, medium-sized star, the kind of star that shows up, does its job reliably for about 10 billion years, and doesn't cause any unnecessary drama. But even a merely competent star is an engine of almost incomprehensible output. Every second, the sun converts roughly 4 million tons of matter into pure energy through nuclear fusion. Every second, not every day, not every hour, every second, 4 million tons of itself becomes light and heat and the gentle solar wind that fills the inner solar system. It has been doing this for 4.5 billion years. It will continue for roughly another 5 billion. The total energy output across that entire lifetime is a number so large that writing it out in full would take more digits than this chapter has words. A gamma-ray burst releases the equivalent of all of that, all 10 billion years of a star's complete output, in somewhere between a fraction of a second and a few minutes. This is what the mathematics produced. This is what the astronomers had to accept. And for a brief, vertiginous moment in the late 1990s, it was not entirely clear that physics could actually accommodate it. The problem, and there was a problem, lay in an assumption so basic that most people making the calculation hadn't even noticed they were making it. The assumption was this, that the burst radiates in all directions equally, like a light bulb, like a star, like most things in the universe that emit energy, which tend to do so in roughly spherical patterns because spheres are what you get when you have no reason to prefer one direction over another. When astronomers calculated the energy of a gamma-ray burst, they assumed the energy was distributed across the full sphere of space surrounding the source, spreading out in every direction simultaneously, thinning as it went according to the familiar mathematics of the inverse square law. If that assumption was correct, the numbers were almost physically absurd. The universe would need to convert an entire stellar lifetime's worth of mass into pure energy and release it simultaneously in every direction. No known mechanism could do that. Theorists were uncomfortable. Some were more than uncomfortable. But what if the assumption was wrong? What if a gamma-ray burst didn't radiate in all directions? What if, instead of a sphere of energy, it produced something much more concentrated? Two tight beams of radiation, firing outward along a preferred axis, like the beams of a lighthouse rather than the glow of a lantern. If the energy wasn't spread across the whole sky but instead confined to a narrow cone, say 1% of the full sphere, then the total energy required would drop by a factor of roughly 100. still extraordinary, still far beyond anything a single star produces in its normal lifetime, but no longer physically impossible, no longer something that made theorists check the calculation 3 times and then go for a slightly longer walk than usual. The lighthouse model, as it became known, transformed the energy problem from a crisis into a challenge. The numbers were still extreme. They were just extreme in a way that physics could, with appropriate effort, begin to explain. So, what produces the beam? The answer requires going back to the source, to the dying star, or the colliding neutron stars, at the origin of the burst. In either case, the central engine of a gamma-ray burst is a newly formed black hole surrounded by a disk of intensely hot, rapidly infalling material. The disk is threaded with magnetic fields of extraordinary strength. As the material spirals inward and the black hole spins, those magnetic fields wind up tighter and tighter, accumulating energy the way a spring accumulates energy when you compress it, until they release, launching 2 jets of plasma outward along the rotation axis of the black hole at speeds that are, quite literally, a substantial fraction of the speed of light. Not fast, not very fast, a substantial fraction of the speed of light. These jets are moving at perhaps 99% of the maximum velocity the universe permits anything to travel, and they are carrying the energy of 10 billion years of solar output, focused into a beam perhaps a few degrees across. The jets punch through the outer layers of the dying star, which, in the case of a long burst, is still technically present, still collapsing, still in the process of becoming a supernova, and emerge into open space. The gamma-ray emission we detect is produced within the jets themselves, through a process of internal collisions, faster material catching up with slower material, producing shock waves that accelerate electrons to extreme energies, which then radiate gamma rays. The chaotic, spiky, never quite the same light curves of gamma-ray bursts. No 2 are identical, each one a different pattern of peaks and troughs, reflect this internal structure. Each spike is a collision. Each collision is a story. Now comes the consequence that changes everything about how we think about gamma-ray burst statistics. If the energy of a gamma-ray burst is confined to a narrow beam, then we can only detect the burst if that beam is pointed at us. The jet has to be aimed even approximately in the direction of Earth. If it's aimed anywhere else, at another galaxy, at an empty patch of intergalactic space, at a region of the universe where there happen to be no astronomers with satellites, we see nothing. The burst happens. The jets fire. The photons race across the universe, and they miss us entirely, and we never know. This is not a small effect. For a typical opening angle of a few degrees, the fraction of the full sky covered by one jet is perhaps half of 1%, which means that for every gamma-ray burst we detect, every burst where the beam happens to be pointing our way, there are something like 200 bursts firing in other directions that we miss completely. 200 events, each releasing the equivalent of 10 billion years of solar energy in a few seconds, occurring in our observable universe for everyone that happens to illuminate our corner of it. The universe is considerably more violent than it appears. We are seeing a tiny, privileged sample of the full carnage. The beams we're catching are the ones that hit us. The rest are sweeping past other galaxies, other empty spaces, completely undetected by anyone. There is something faintly humbling about this. We have built satellites, developed exquisitely sensitive detectors, spent decades solving the localization problem, and we are still only catching the bursts that happen to be aimed at us. The majority of the universe's most energetic events are occurring without our knowledge, in directions we are not looking, hitting places that are not here. The cosmos is indifferent to our detection networks in a way that is, if you let yourself think about it, genuinely vertiginous. The afterglow, it turns out, is the key to knowing the beam exists at all. Here is the difficulty with the beaming hypothesis. If we can only see the burst when the jet is pointed at us, how do we ever know the jet has a finite width? How do we measure the opening angle? We can't see the edges of the beam directly. We're inside it, looking back along it. The geometry doesn't allow us to step sideways and measure. The afterglow solves this elegantly. As the jet ploughs into the surrounding interstellar medium after the burst itself has ended, it drives an expanding shock wave through the gas. Initially, the shock wave is moving so fast that relativistic effects cause it to appear much wider than it really is, a quirk of the mathematics of special relativity that makes a narrow beam look, from our perspective, like it subtends a much larger angle than it actually occupies. But as the jet decelerates, as it dumps its energy into the surrounding material and slows down, this relativistic illusion fades. At a certain point in the deceleration, the true edge of the jet becomes apparent to our instruments. And when it does, the afterglow fades more rapidly than expected. There is a kink in the light curve, a sharp steepening in the rate of decline that marks the moment the jet's true geometry reveals itself. This is called the jet break, and it is one of the more satisfying pieces of detective work in modern astrophysics. The moment when the afterglow, fading across days and weeks, quietly confesses the shape of the explosion that produced it. By measuring when the jet break occurs and how steep it is, astronomers can calculate the opening angle of the jet, and from the opening angle, the true energy of the burst. The lighthouse beam, measured not by seeing its edge directly, but by watching what happens when the lighthouse slows down. The corrected energy figures are lower than the isotropic estimates, sometimes considerably lower by factors of hundreds. But lower is a relative term when you started at almost physically impossible. Even corrected for beaming, the most energetic gamma-ray bursts release more energy in their jets than any other known phenomenon in the universe. A typical long burst, with its energy concentrated into a beam a few degrees wide, is releasing something in the range of 10 to the power of 44 joules. That number requires some context. It is roughly equivalent to the total energy released by the Sun across 2,000 years, compressed into a few seconds and fired in one direction. The corrected figures are extraordinary. They are just extraordinary in a way that physics can, after considerable theoretical effort, begin to make sense of. This is, in the end, how science tends to work, not with neat answers that arrive pre-packaged and comfortable, but with successive approximations, each one more accurate than the last, each one revealing a universe that is stranger and more extreme than the previous version suggested, each one replacing one set of questions with a different, usually harder set. The energy crisis of the late 1990s was resolved not by the universe becoming less violent, but by our understanding of its geometry becoming more precise. The bursts are real, the energy is real, the beams are real, the lighthouses are sweeping the cosmos in every direction, most of them missing us entirely. A few of them, just a few, catching our instruments at exactly the right moment. The ones that find us have been travelling for billions of years to do so. That seems worth appreciating, in the quiet of wherever you are right now. Every star, from the moment it ignites, is losing an argument. The argument is between gravity and fire, between the inward pull of an object's own mass, which has been trying to collapse it since before it was properly a star at all, and the outward pressure of nuclear fusion, which releases enough energy to hold that collapse at bay for as long as the fuel lasts. It is not a subtle conflict, the forces involved are almost incomprehensibly large. The stakes for the star in question are absolute, and the outcome for every star that has ever existed is never really in doubt. Gravity is patient in a way that fire is not. Fire needs fuel. Gravity needs nothing. It simply waits. For a star like our Sun, the wait is a comfortable 10 billion years. Our Sun is, in this sense, lucky, or at least well-proportioned. It has enough hydrogen to keep the fusion going for a very long time, and it burns through that hydrogen at a rate that is steady rather than frantic. It will live long enough for planets to form, for life to arise and diversify, for creatures to evolve who will spend some of their evenings lying in the dark and thinking about stars. It is a generous, unhurried kind of star. The stars that produce gamma-ray bursts are not that kind of star. What we are interested in tonight are the massive ones, the stars born with 20, 30, 50, and sometimes 100 or more times the mass of our Sun, compressed into objects that burn with a ferocity that makes our own star look like a nightlight. These stars are not unhurried. They are the opposite of unhurried. Under the crushing pressure of their own gravity, their cores reach temperatures so extreme that they tear through their hydrogen fuel, not in billions of years, but in millions. A star with 30 times the mass of the Sun might exhaust its core hydrogen in 3 million years. In astronomical terms, that is not a long career. But here is the thing about massive stars. When their hydrogen runs out, they don't simply stop. They adapt, or rather, they are forced to adapt because gravity is still there, still pushing inward, and the only alternative to adapting is collapsing. So the core contracts slightly, heats up further, and ignites the next available fuel, helium. When the helium is exhausted, the core contracts again and burns carbon, then neon, then oxygen, then silicon, each stage briefer than the last, each stage producing less energy for the same amount of fuel, each stage buying a little less time against the eventual outcome. By the time a massive star is burning silicon in its core, it has perhaps a few days left. The outer layers, still burning through earlier fuel stages in concentric shells, like a cosmic onion of escalating desperation, have expanded to dimensions that would swallow our entire inner solar system. But inside, at the center, something is accumulating that signals the end of everything. Iron. Iron is where stellar fusion goes to die. Every element the star has burned so far, hydrogen, helium, carbon, all the way up through the periodic table to silicon, releases energy when fused into heavier elements. That's the whole point. That's what fusion is, the conversion of lighter nuclei into heavier ones, with a small amount of mass converted into energy in the process, and that energy providing the pressure that holds the star up. But iron is different. Iron sits at the bottom of the nuclear binding energy curve, the point of maximum stability. Fusing iron into heavier elements does not release energy. It consumes it. The star cannot burn iron. Iron simply accumulates, inert and increasingly heavy, at the center of the collapsing hierarchy. When the iron core grows large enough, roughly 1.5 times the mass of the Sun, compressed into a sphere about the size of Earth, it reaches a critical point. The electrons that have been holding it up, providing a quantum mechanical pressure called electron degeneracy, can no longer do so. The core becomes unstable. What happens next takes less than a second, and it is important to understand what less than a second means here. Not a leisurely second. Not the kind of second that passes while you're thinking about what to say next. A fraction of a second, perhaps a tenth, perhaps less, in which the iron core of a star that has been burning for millions of years simply falls inward. The collapse is so complete and so rapid that the core goes from roughly Earth-sized to roughly city-sized in the time it takes a single heartbeat to begin. What stops the collapse, for most stars at this point, is a new kind of pressure. As the core compresses beyond the density of an atomic nucleus, the neutrons that now make up most of the material resist further compression with a force called neutron degeneracy pressure. The core essentially becomes an enormous atomic nucleus, 20 kilometers across, with the density of nuclear matter throughout. It bounces. The bounce is not gentle. The infalling outer layers of the star, which have been accelerating downward for a fraction of a second at velocities approaching a quarter of the speed of light, slam into this suddenly rigid core and rebound with almost inconceivable violence. A shock wave tears outward through the rest of the star, supplemented by a flood of neutrinos pouring out of the collapsing core in such enormous quantities that even the extraordinarily thin soup of stellar material above it absorbs enough of them to add further energy to the explosion. The result is a supernova, one of the brightest events the universe produces, capable of briefly outshining the entire galaxy in which it occurs. For most massive stars, this is the end. The outer layers are blasted away. A neutron star is left behind, that city-sized sphere of nuclear density material, spinning rapidly, cooling slowly, gradually fading from the scene. The star is gone. The neutron star remains. But for the most massive stars, even this is not the end. For stars that began with the right, or rather the wrong, combination of mass and structure, the collapse doesn't stop at the neutron star stage. Gravity is too strong, the mass too great, the neutron degeneracy pressure insufficient. The collapse continues, and what it produces instead of a neutron star is a black hole. This is where the gamma-ray burst begins, or rather, this is where the machinery that produces it begins to assemble itself. A newborn black hole formed in the collapsing core of a massive star is surrounded by chaos. The outer layers of the star are still falling inward. Material from the inner regions, rather than escaping in the supernova shockwave, is being captured by the black hole's gravity and forming a disk. An accretion disk of dense, hot, rapidly rotating gas, swirling around the black hole the way water swirls around a drain, except at temperatures of billions of degrees and with magnetic fields of extraordinary strength threading through it. The black hole spins, the disk spins, and the magnetic fields, tangled and compressed and wound tight by all this rotation, do something remarkable. They act as an electromagnetic catapult, extracting energy from the spinning system and launching it outward along the rotation axis, the only direction in which the infalling material isn't blocking the path. Two jets of plasma, accelerated by these magnetic fields to within a fraction of a percent of the speed of light, punch upward and downward through the star, following the path of least resistance along the poles. The jets have to travel through the outer layers of the star before they reach open space. This is not trivial. The star is large, even a stripped-down Wolf-Rayet star, which is the typical progenitor of a long gamma-ray burst, is still many times the size of our Sun. The jets bore through this material like enormous, impossibly energetic drills, depositing energy into the surrounding stellar material as they go, heating it, disrupting it, punching a channel through it. This takes a few seconds, perhaps 10, perhaps 30. Then the jets break free. They emerge from the surface of the dying star and erupt into the interstellar medium, carrying their extraordinary energy payload with them, and in the turbulent, structured, fast and slow material colliding environment within the jets. The gamma rays are produced in those internal shocks, faster material overtaking slower material, electrons accelerated, photons emitted, the light curve spiking and fading and spiking again in a pattern that is unique to every burst, as individual as a fingerprint. The dying star, meanwhile, does not go quietly in any other respect either. The supernova, what remains of the explosion after the jets have taken their energy and departed, is still one of the most energetic events in ordinary stellar astronomy. The outer layers, blasted free by the shock wave and the neutrino flood, expand outward into the surrounding space over days and weeks, glowing with the light of billions of degrees, and then cooling gradually into the kinds of expanding nebulae that astronomers photograph with great enthusiasm and use for desktop backgrounds. But the supernovae associated with gamma-ray bursts are not ordinary supernovae. They are hypernovae, a classification reserved for core collapse supernovae at the extreme end of the energy spectrum, roughly 10 to 100 times more energetic than a standard supernova, and distinguished by the particular chemical signatures left in the expanding debris. Astronomers have caught several gamma-ray burst afterglows fading away, while a hypernova brightened beneath them. The burst in gamma rays followed by the explosion in visible light. The two events united in a single stellar death, observed at different wavelengths on different timescales. This is the smoking gun that tied long gamma-ray bursts definitively to the deaths of massive stars. The burst and the hypernova are not separate events happening to coincide. They are the same event, seen in different light. Which brings us to a detail that matters more than it might initially seem: the progenitor star's wardrobe. A massive star in its final stages typically retains an outer envelope of hydrogen, the original material from which it formed, sitting above all the subsequent fusion products, puffing the star out to enormous dimensions. These stars are called red supergiants, and they are genuinely enormous. If you placed one at the center of our solar system, it would engulf everything out to the orbit of Jupiter and possibly Saturn, and it would do so without any particular urgency because it is a red supergiant, and red supergiants are not known for their urgency. The problem with a red supergiant as a gamma-ray burst progenitor is that outer hydrogen envelope. The jets, boring their way through the star, would have to punch through an enormous amount of additional material before reaching open space. Many models suggest the jets would be smothered. Choked by the sheer volume of material above them, their energy dissipated before they could escape. No breakout, no gamma-ray burst, just a somewhat unusual supernova, and a frustrated jet depositing its energy uselessly inside the star. What the models favour instead is a star that has already shed its hydrogen envelope, blown away by the intense stellar winds that massive stars generate throughout their lives, or stripped by a companion star in a binary system. What's left is the hot, dense, compact core, a Wolf-Rayet star, named for the French astronomers Charles Wolf and Georges Rayet, who first identified this class of object in 1867, and presumably went home that evening, feeling they had done a solid day's work, without fully appreciating quite what they had found. A Wolf-Rayet star provides the jets with a fighting chance. The envelope is gone. The path to open space is shorter. The jets bore through the remaining material in seconds rather than being extinguished by it. They break out, and the burst begins. There is something worth sitting with about what a gamma-ray burst actually represents in the life of a star. A massive star burns for millions of years, not long by cosmic standards, but a genuine span of time by any other measure. It forges heavy elements in its core, cycling through the periodic table in stages, building up the raw material of chemistry and, eventually, of biology. It lives brilliantly and briefly, giving off more light in 1,000,000 years than our sun will produce in 10 billion. And then it dies. The death takes a fraction of a second in its most critical phase. The core falls, the black hole forms, the jets fire, the gamma rays race outward across the universe. Everything the star spent millions of years building, the iron core, the layered shells of successively heavier elements, is compressed, disrupted, blown apart, and scattered into the surrounding space. The heavy elements, freed from the star, join the interstellar medium. They become the raw material for the next generation of stars, the next generation of planets, the next generation of everything. The most violent part of a star's existence lasts a few seconds. The consequences of those seconds propagate for billions of years. The universe has a way of making the brief things matter most. Somewhere above the Earth, a satellite has just detected something. The instruments registered it at precisely the moment it arrived, a pulse of gamma rays, intense and brief, lasting perhaps 12 seconds before fading back into the background noise of the cosmos. The onboard software has already done its initial analysis. The burst is real, not an instrumental artifact, not a charged particle striking the detector at an inconvenient angle. A real gamma-ray burst from somewhere out there in the universe has just announced itself. The satellite knows roughly where in the sky it came from. Not precisely, but roughly, a region, a patch. Somewhere in that direction, billions of light years away, something extraordinary has just happened. And now, the clock is running. The afterglow, the fading X-ray and optical emission that follows the burst itself, the thing that makes the event scientifically useful rather than merely spectacular, is already dimming. It will be bright enough to study properly for perhaps a few hours. After that, it will require increasingly large telescopes to detect at all. After a few days, only the most powerful instruments on Earth will be able to see it. After a few weeks, it will be gone entirely, indistinguishable from the background glow of its host galaxy. Every second of delay is a second of brightness lost. Every minute spent on paperwork is a minute the universe spends quietly erasing the evidence. The race has already begun, and depending on which decade of gamma-ray burst astronomy we are standing in, the race is either going very badly, somewhat better, or, finally, thrillingly, being won. For the first 30 years after the discovery of gamma-ray bursts, it went very badly. The fundamental difficulty was a mismatch between the timescale of the event and the timescale of the human response. A gamma-ray burst lasts seconds. The process of detecting it, calculating a position, communicating that position to astronomers, and getting a telescope pointed at the right patch of sky took, in the 1970s and 1980s, hours, sometimes days. By the time anyone managed to look, the afterglow that theory suggested should be there had faded beyond the reach of available instruments or hadn't been caught at all, and the field was left with nothing but the memory of a signal and a patch of sky that looked stubbornly ordinary. This was deeply, professionally frustrating. Imagine spending your career studying the most energetic events in the universe while being structurally prevented from ever actually looking at one properly. The bursts were real. The afterglows were almost certainly real. The information they carried, distances, energies, the physics of the explosion itself, was irreplaceable, and it was dissolving quietly and persistently before anyone could capture it. The field needed speed, it needed precision, it needed, in short, a completely different approach to the problem of how to catch something that doesn't wait. The first serious attempt at a coordinated solution was characteristically improvised. The interplanetary network, which we met briefly earlier tonight in its role as a triangulation tool for improving burst positions, was not built for speed. It was built from spare parts. Spacecraft designed for planetary science, solar observation, and various other missions that happened to carry gamma-ray detectors as secondary instruments. Correlating their detections to produce improved positions required careful analysis of timing data from multiple sources, and the process took time, hours, sometimes days, which rather defeated the purpose if what you wanted was to catch a fading afterglow. But the positions it produced, when they eventually arrived, were better than what a single satellite could achieve. Better meant smaller error boxes. Smaller error boxes meant optical searches that were, at least in principle, feasible. The network was not the solution. It was the proof that a solution existed if only the right tools could be built. BeppoSAX, as we've established, provided the first genuine breakthrough, the ability to localize a burst precisely enough within a few hours that an optical counterpart could be found and studied. For a few years in the late 1990s and early 2000s, this was the state of the art, a detection in gamma rays, a rapid pivot to X-ray follow-up, a position good enough for ground-based telescopes to search, and a frantic scramble by the astronomical community to get their instruments pointed at the right piece of sky before the afterglow faded. The scramble was real. Astronomers who worked in this period describe a peculiar rhythm to their lives, the burst alert arriving at any hour, the rapid calculations, the calls to observatories in whichever part of the world was currently experiencing night, the tense wait to see if the afterglow was still bright enough to study. There was urgency to it that most branches of astronomy, which tend to involve patient observation of things that have been there for billions of years and will continue to be there next Tuesday, do not typically require. Gamma-ray burst astronomy in the BeppoSAX era had a quality of emergency that its practitioners found, depending on their temperament, either exhilarating or exhausting. Often, both simultaneously. But BeppoSAX had limitations. It could only observe a small fraction of the sky at any one time. Its response was rapid by the standards of what had come before, but not rapid enough to catch the very earliest, brightest phases of the afterglow. And it was a single satellite, doing its best, covering what it could. The field needed something purpose-built, something designed from the outset around the specific problem of catching gamma-ray burst afterglows as quickly as possible. In November 2004, NASA launched SWIFT. SWIFT is, in the quietly understated way of spacecraft names, named for its defining characteristic. It is fast. Not fast in the sense of moving quickly through space. All satellites move quickly through space because orbital mechanics requires it. But fast in the sense of response. SWIFT can detect a gamma-ray burst, calculate its position using an onboard X-ray telescope, and rotate the entire spacecraft to point its ultraviolet and optical instruments at the source in approximately 90 seconds. Not 90 minutes, not 90 hours, 90 seconds. This sounds straightforward until you consider what it actually involves. A satellite in low Earth orbit is a precision instrument moving at roughly 7.5 kilometers per second, rotating it rapidly, accurately to a new pointing direction, while keeping its solar panels oriented toward the sun, its antennas pointed toward ground stations, and its sensitive instruments protected from accidental exposure to bright sources, is an engineering challenge of considerable complexity. The team that designed SWIFT's attitude control system solved this challenge so effectively that the spacecraft can slew to a new target faster than most ground-based telescopes can manage. It is, in this respect, genuinely extraordinary. But the rotation is only the beginning of what makes SWIFT transformative. Within seconds of detecting a burst, SWIFT broadcasts the coordinates automatically. No human decision required, no waiting for a scientist to review the data and make a judgment call. The gamma-ray burst coordinates network, known as the GCN, receives the alert and distributes it to subscribers worldwide in under a minute. Observatories receive it. Robotic telescopes receive it. Astronomers' phones receive it. The alert goes everywhere simultaneously, and the response begins. The response in the SWIFT era is something worth imagining in some detail. It is 3 o'clock in the morning in Santiago, Chile. The Very Large Telescope, 4 enormous mirrors, each 8.2 meters across, perched on a mountaintop in the Atacama Desert, is in the middle of a scheduled observation program. A spectrograph is recording the light from a distant quasar. The night is clear. The seeing is excellent. The telescope operator is managing the queue of observations with the quiet efficiency of someone who has done this many times before. Then the alert arrives. The coordinates come through automatically. The burst was detected 43 seconds ago. The X-ray afterglow is already fading. The GCN alert identifies the position to within a few arcseconds, a tiny patch of sky, small enough to search with a single telescope pointing. The observation queue is interrupted. The massive telescope swings, slowly given its size, but with impressive precision, to the new coordinates. The spectrograph, which was recording the quasar, is now recording whatever lies at the burst location. What it finds, if the response is fast enough and the afterglow is bright enough, is a point of light that wasn't there before, fading even as the telescope watches it, and in the spectrum of that fading light, in the pattern of wavelengths absorbed and emitted as the afterglow passes through the gas of its host galaxy, and the intergalactic medium between it and us, lies an extraordinary quantity of information. The distance to the burst, encoded in the redshift, the chemical composition of the gas along the line of sight, the properties of the explosion itself, written in light that has been travelling for billions of years and will be legible for only a few more hours before it dims below detection. This is why the phone goes off at 3 in the morning. This is why the observation queue gets interrupted. The information is perishable in a way that most astronomical information is not, and the window for collecting it is measured in hours. Robotic telescopes have added another dimension to this response network that deserves particular attention, partly because they are genuinely remarkable, and partly because they do something that no human-operated telescope can quite match. They respond without hesitation. A robotic telescope is exactly what it sounds like. An automated observatory that operates without a human at the controls, responding to alerts, making observations, and storing data according to a set of instructions written in advance by the scientists who designed it. When a GCN alert arrives, the robotic telescope doesn't need to wake anyone up. It doesn't need to consult a schedule or navigate institutional procedures, or wait for a senior astronomer to approve the interruption. It simply pivots, points, and begins collecting light, often within 30 seconds of the alert being issued. Some of the fastest robotic responses have caught gamma-ray burst afterglows, while they were still extraordinarily bright. In the first minutes after the burst, when the afterglow is sometimes visible with equipment no more sophisticated than a good amateur telescope. One remarkable afterglow, from a burst detected in 2008, reached a peak optical brightness that would have made it briefly visible to the naked eye from Earth if anyone had happened to be looking in the right direction at the right moment. Nobody was, as it turned out, because the right direction was a fairly nondescript patch of sky with no prior reason to attract attention. But the robotic telescopes caught it, and the data from those first minutes was extraordinary. Fermi, launched in 2008, extended the network's reach in a different direction. Where Swift trades wide-field sky coverage for rapid, precise follow-up, Fermi's Large Area Telescope surveys a large fraction of the sky simultaneously, detecting bursts across a broader range of gamma-ray energies than Swift's Burst Alert telescope was designed to cover. The two satellites are complementary rather than competitive. Swift catches bursts and rapidly localizes them for follow-up, while Fermi provides the broader context of the gamma-ray emission itself, including the highest energy photons, which carry particular information about the physics of the jet. Together, Swift and Fermi have made gamma-ray burst astronomy something that would have been almost unrecognizable to the scientists who spent the 1970s and 1980s staring at empty error boxes and wondering if the afterglow they were looking for had ever been bright enough to find. Between them, they detect several hundred bursts per year. Afterglows are caught routinely. Redshifts are measured regularly. The distance, energy, and host environment of each burst become part of a growing database that is allowing astronomers to study these events statistically, not as rare, irreproducible mysteries, but as a population with properties that can be measured and modelled. There is something in this story, in the arc from the Cold War satellites that stumbled onto these events by accident, through the decades of frustrating near misses to the purpose-built network of spacecraft and robotic telescopes that now catches them routinely, that feels like a particularly human kind of progress. Not the clean linear progress of textbook science where each discovery follows logically from the last and the path forward is always clear. The messier, more honest kind, the kind that involves 30 years of working with inadequate tools, the kind that requires international collaborations and improvised solutions and satellites named Bepper-Sachs, the kind where the breakthrough, when it comes, arrives not from one heroic insight, but from the patient accumulation of better instruments and better methods, and a community of scientists who refused to accept that the most energetic events in the universe were simply going to remain unstudied, because they had the inconvenience of fading before anyone could look at them properly. The gamma-ray burst that fired its jets into the cosmos tonight, and statistically there was almost certainly one, was caught. Not by luck and not by accident, but because someone built Swift, and someone built Fermi, and someone wrote the software that broadcast coordinates in under a minute, and someone designed robotic telescopes that respond in 30 seconds, and someone chose to interrupt the observation queue in Santiago at 3 a.m. The fading ember was found. It always is now. We have, so far, been spending our time with the long bursts. The ones that last for more than 2 seconds, sometimes for minutes, and that trace their origins to the deaths of massive stars, the Wolf-Rayet progenitors stripped of their hydrogen envelopes, the collapsers drilling their jets through stellar material and erupting into space with the energy of 10 billion years of solar output. These are the bursts that Beppo-Sachs first localized, that Swift now catches routinely, that have given us distances and redshifts and host galaxies, and all the data that has built gamma-ray burst astronomy into a mature science. They are spectacular, and they are well understood, and in a field that spent 30 years struggling to learn anything about these events at all, well understood feels like an extraordinary achievement. But there is a second population. We mentioned it earlier tonight, and it has been waiting patiently since then, as its members tend to do. the short bursts, the ones lasting less than 2 seconds, the ones that live in old, quiet galaxies where the frantic business of star formation ended long ago, the ones whose origin, for a long time, was genuinely mysterious. Not in the exciting way where you have several competing hypotheses and rich observational data to distinguish between them, but in the more uncomfortable way where the data was sparse, the hypotheses were speculative, and the thing producing these events had the frustrating property of being completely invisible, right up until the moment it exploded. What was sitting in those old, quiet galaxies patient across billions of years? 2 dead stars, orbiting each other, falling with exquisite slowness toward the most violent possible reunion. To understand what a neutron star is, it helps to have already made peace with the fact that the universe is considerably denser than everyday experience suggests. You are, at this moment, made of atoms. Atoms are mostly empty space, a tiny nucleus surrounded by a cloud of electrons so thin and so sparse that if you scaled a hydrogen atom up to the size of a football stadium, the nucleus would be a marble at the center, and the electron would be somewhere in the upper tiers, and everything in between would be nothing at all. This is slightly disconcerting when you first encounter it, given how solid the floor feels underfoot. The solidity is an illusion produced by electromagnetic forces. The electrons in the floor repelling the electrons in your feet with enough vigor to prevent you from passing through. You are not resting on matter. You are resting on a force field produced by matter. The matter itself is almost entirely absent. A neutron star takes this already counterintuitive situation and makes it considerably more so. When a massive star's core collapses, and the mass is not quite sufficient to form a black hole, something extraordinary happens to the atomic structure of the material. The electrons, under the enormous pressure of the collapse, are forced into the protons. Electrons and protons, pressed together with enough energy, combine to form neutrons. The entire core, a mass greater than the Sun, transforms into a sphere of pure neutrons, roughly 20 kilometers across, with no empty space between them. No electron clouds, no nuclei separated by vast voids. Just neutrons, packed together at nuclear density throughout. To give this some texture, a single teaspoon of neutron star material would weigh approximately 400 million tons on Earth. You would not want to drop it, and not primarily for the damage it would cause on impact, though that would also be considerable, but because there is no material in existence from which you could make a teaspoon capable of holding it. The teaspoon would be crushed into the same neutron-dense state as its contents before it reached the surface. The teaspoon in this scenario is very much part of the problem. A neutron star spins. This is not a choice. It is conservation of angular momentum, the same principle that makes a spinning ice skater rotate faster when they pull their arms in. The collapsing core of a massive star was rotating, and when it compressed from something roughly Earth-sized to something city-sized, all that rotational momentum concentrated into a much smaller object, producing spin rates that are genuinely difficult to hold in the mind comfortably. The slowest neutron stars rotate a few times per second. The fastest, the millisecond pulsars, spun up by accreting material from a companion star over millions of years, rotate hundreds of times per second. The record holder completes 716 full rotations every second. Its equatorial surface is moving at roughly a quarter of the speed of light. It has been doing this continuously, without apparent effort or inconvenience, for longer than recorded human history. The neutron star is not tired. The neutron star will not become tired. The neutron star has opinions about endurance that make any human athletic achievement look like a mild warm-up. As it spins, the neutron star sweeps beams of radiation from its magnetic poles across the surrounding space, the lighthouse effect that gives pulsars their name, each rotation producing a detectable pulse of radio waves if the beam happens to cross the Earth. It was the extraordinary regularity of these pulses that initially confused the astronomers who discovered them in 1967. The signal was so precise, so clock-like, that for a brief and slightly embarrassed period, the source was labelled LGM1, Little Green Men 1, before the rotating neutron star explanation arrived, and everyone quietly agreed not to mention the earlier hypothesis at conferences. Now, place two of these objects in orbit around each other. This is not as contrived a scenario as it might sound. Stars frequently form in binary systems, two stars born from the same collapsing cloud of gas, orbiting their common centre of mass from the moment of formation. If both stars are massive enough, both will eventually undergo supernova explosions and leave neutron star remnants. If the system survives both explosions without flying apart, which requires a particular combination of masses and orbital geometry, and is somewhat unlikely but not vanishingly so, the result is a binary neutron star system, two of the densest objects in the universe, orbiting each other in a dance that is, on the timescale of human civilization, essentially unchanging. The orbital periods of known binary neutron star systems range from a few hours to a few days. The two stars are separated by distances comparable to the radius of our Sun, close on astronomical scales but not touching, not yet. Each system is a pair of city-sized objects, each containing more mass than the Sun, wheeling around each other in the dark. Here is where patience becomes relevant in a way that should by now feel appropriately cosmic. As two neutron stars orbit each other, they lose energy. Not through friction, there is nothing to create friction in the vacuum between them, but through the emission of gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, produced by any accelerating mass, radiating outward from the system and carrying energy away with them. We will spend more time with gravitational waves soon, but for now it is enough to know this. They are real. They carry energy, and their production causes the orbiting system to lose that energy from its orbit. As energy drains from the orbit shrinks. The two neutron stars move closer together. Their orbital period shortens. They move faster. They generate stronger gravitational waves, which carry away energy faster, which causes the orbit to shrink faster, which generates stronger waves. The process is self-reinforcing, not dramatically at first, but inexorably. The in-spiral has begun. For a newly formed binary neutron star system, the in-spiral takes time. A great deal of time, hundreds of millions of years, billions of years in some cases, while the Earth formed, while life arose in its oceans, while the dinosaurs evolved and were extinguished and mammals inherited the planet, and one branch of those mammals eventually developed the cognitive capacity to worry about neutron star mergers. The in-spiral continued, patient, mathematical, indifferent to everything happening in the neighborhood. The two stars inch closer together across geological time. Their separation shrinks from something comparable to the Sun's radius, to something comparable to the Earth's radius, to something comparable to the Moon's distance from Earth, to something far less than that. The orbital period, which began at hours, shrinks to minutes, then seconds. The gravitational wave emission, which began as a whisper, builds toward a roar. In the final seconds of the in-spiral, The two neutron stars are moving at a significant fraction of the speed of light. They are separated by tens of kilometers. Their combined gravitational field is distorting the space-time around them so severely that the geometry of the region bears little resemblance to the flat, well-behaved space-time we inhabit. The gravitational waves they are now producing are not a whisper. They are a screech, a rapidly rising chirp of gravitational radiation, climbing in frequency and amplitude toward a peak that corresponds precisely to the moment of contact. Then they touch. The merger takes milliseconds. Two objects, each containing more mass than the Sun, each 20 kilometers across, collide at a velocity that would carry you from one side of the Earth to the other in a fraction of a second. The collision is not gentle. There is no word in the language of gentle things that applies here. The neutron star material, those packed, pressure-stabilized neutrons, held in their configuration by quantum mechanical forces that have successfully resisted compression for billions of years, is suddenly subjected to pressures and temperatures that exceed anything that has existed in the universe since the earliest moments after the Big Bang. The result is a kilonova, an explosion powered not by nuclear fusion but by the radioactive decay of newly synthesized heavy elements, glowing in optical and infrared light for days. We will return to what those elements are next, because it is one of the most extraordinary things in this entire story. And accompanying the kilonova, launched in the first fractions of a second of the merger, is a jet of gamma rays, brief, intense, aimed along the rotation axis of the merged system, a short gamma ray burst. The short burst lasts less than 2 seconds, often less than 1. The merger that produces it has been building for 1 billion years. There is a particular quality to this disproportion that I find worth dwelling on. We are not talking about an explosion that takes a long time to prepare in any conventional sense. A bomb being assembled, a volcano accumulating pressure. We are talking about two objects, each the remnant of a star's entire lifetime, spending 1 billion years of orbital decay to arrive at a collision that lasts a millisecond. The ratio of preparation to event, 1 billion years to a millisecond, is so extreme that normal intuition cannot accommodate it. It is as if every human being who has ever lived spent their entire life walking toward a single doorway, and the doorway itself opened and closed in less time than it takes to blink. And then it is over. The merged remnant, which may briefly be a hypermassive neutron star before collapsing to a black hole, or may collapse to a black hole immediately, depending on the combined mass, settles into whatever its final state will be. The kilonova glows and fades. The short gamma-ray burst races outward in its narrow beam, crossing whatever distance separates the merger from us, arriving at swift or Fermi days or years or billions of years later. The old, quiet galaxy that hosted the merger goes back to being old and quiet. It has been waiting for this event since the neutron stars formed. Now it has happened, and the galaxy returns to the patient business of aging gracefully, as old, quiet galaxies do. What the short burst leaves behind in the debris of the merger is what really matters. But that is a story for later tonight, and it involves gold, and it is worth waiting for. For now, let us simply note that two of the most extreme objects in the universe, objects so dense that a teaspoon of their material would outweigh every car ever manufactured, objects spinning hundreds of times per second, objects that have been falling toward each other since before the Earth existed, can find each other across the dark and complete their journey in a flash of light that lasts less than the time it takes to say the word collision. The universe is patient, but when it finally acts, it does not hesitate. For all of human history, we have been looking at the universe. Everything we have ever learned about the cosmos, every galaxy catalogued, every planet discovered, every stellar death observed, every distance measured, has arrived at us as light. Not always visible light, the narrow band of wavelengths our eyes evolved to detect. Radio waves, infrared, ultraviolet, X-rays, gamma rays. All of these are forms of electromagnetic radiation, all of them travelling at the speed of light, all of them variations on the same fundamental phenomenon. Different wavelengths, different energies, different instruments required to catch them, but fundamentally the same thing. The universe, communicating with us through light. For 100,000 years of human existence, this was the only channel available, the only sense through which the cosmos could speak, and we could listen. On the 14th of September 2015, that changed. Gravitational waves are not light. They are not electromagnetic radiation of any kind. They are something categorically different. Distortions in the fabric of space-time itself, propagating outward from massive accelerating objects, the way ripples propagate from a stone dropped into still water. Where light is a disturbance in electromagnetic fields, gravitational waves are a disturbance in the geometry of the universe. They stretch space in one direction while compressing it in the perpendicular direction, oscillating back and forth as they pass, at the speed of light, through everything in their path. Everything, importantly, includes the Earth, and the detectors on it, and the scientists inside those detectors who spent decades building instruments sensitive enough to catch something that, by the time it reaches us from across the universe, has been diluted to a distortion smaller than 1/10,000th of the diameter of a proton. Let that sit for a moment. A proton is already incomprehensibly small, roughly a femtometer across, a millionth of a billionth of a meter. 1/10,000th of that is a number so far below the threshold of everyday intuition that comparisons become almost meaningless. And yet this is the signal that LIGO, the Laser Interferometer Gravitational Wave Observatory, was built to detect. Not because anyone thought it would be easy, because it was the only way. LIGO consists of two facilities, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers. Each facility is an L-shaped structure with two arms, each arm 4 kilometers long, meeting at right angles. A laser beam is split at the junction, sent down both arms simultaneously, reflected off mirrors at the far ends, and recombined at the junction. Under normal conditions, flat space-time, no gravitational wave passing through. The two beams travel exactly the same distance and arrive back at the junction simultaneously, cancelling each other out in what is called destructive interference. The detector reads 0. When a gravitational wave passes through, it stretches one arm and squeezes the other by a tiny, oscillating amount. The two beams no longer travel exactly the same distance. They arrive back at the junction fractionally out of phase with each other. The destructive interference is incomplete. The detector reads something other than 0. What LIGO reads in practice is a displacement of roughly 1/10,000th of a proton diameter in a 4-kilometer arm. The engineering required to achieve this sensitivity is staggering. The mirrors at the ends of the arms weigh 40 kilograms each and are suspended from chains of pendulums to isolate them from ground vibration. The laser is stabilized to a precision that makes calling it merely stable feel like an understatement. The vacuum inside the arms is one of the best vacuums ever achieved on Earth. Better than the vacuum in low Earth orbit, because even the tiny pressure of residual gas molecules would introduce noise. The entire apparatus sits on active vibration isolation systems that filter out everything from passing lorries to distant earthquakes to, at one memorable point, a particularly vigorous thunderstorm in Louisiana that arrived at exactly the wrong moment during a test run. The gravitational wave that LIGO detected on the 14th of September 2015, the very first ever detected, from two merging black holes 1.3 billion light-years away, produced a signal that lasted less than a second. The chirp, as it was called, rose rapidly in frequency and amplitude as the black holes spiraled together, peaked at the moment of merger, and then faded. When the LIGO team converted the signal to sound and played it through speakers at the press conference announcing the discovery 6 months later, it sounded like a brief, ascending tone. A single soft thump that lasted perhaps a fifth of a second. Physicists in the audience wept. This seems exactly right. The detection of gravitational waves from merging black holes was extraordinary, but black holes by their nature produce no light. The merger was invisible to every electromagnetic telescope in the world. No optical counterpart, no X-ray glow, no gamma-ray burst. LIGO had heard the universe do something that no eye, however enhanced, could see. It was a new sense, opening onto a cosmos that had previously been entirely silent to us. What the field needed next, what would transform gravitational wave astronomy from a spectacular proof of concept into a genuinely multi-dimensional science, was an event that produced both gravitational waves and light. Something that spoke in both languages simultaneously, allowing astronomers to cross-reference, to confirm, to triangulate, to extract the maximum possible information from a single event using every tool available. What the field needed, in short, was a neutron-star merger. At 12:41 and 4 seconds Coordinated Universal Time, on the 17th of August 2017, LIGO detected a gravitational wave signal unlike anything it had caught before. The signal lasted nearly a minute. Previous detections from merging black holes had lasted fractions of a second. The black holes were massive, their final in-spiral brief and violent. This signal was longer, rising more slowly in frequency, lingering in the detector with the character of something lighter and slower coming together. The waveform matched the theoretical predictions for two inspiraling neutron stars with extraordinary precision. The combined mass of the two objects, roughly 2.7 times the mass of the Sun, was exactly consistent with a neutron-star binary. LIGO and its European counterpart Virgo, which had joined the network 2 weeks earlier and was detecting this event simultaneously, triangulated a position pointing toward a region of sky containing the galaxy NGC 4993, about 130 million light-years away. The event was designated GW170817, the GW for gravitational wave, the numbers for the date. Astronomical naming conventions are not celebrated for their poetry, but they are precise, and precision on the 17th of August 2017 was very much what the situation called for. 1.7 seconds after the gravitational wave signal ended, 1.7 seconds, a gap small enough to fit in a heartbeat, the Fermi satellite detected a gamma-ray burst. A short burst, weak by the standards of the events we have been discussing. 130 million light-years is close, as gamma-ray bursts go, but the burst was still fainter than many detected at far greater distances, suggesting it was either intrinsically less energetic or that the jet was not pointed directly at us. But unmistakable, real, arriving from the same direction as the gravitational waves, at very nearly the same time. The same event, two different phenomena, two different physical processes, one producing gravitational waves, distortions in space-time propagating at the speed of light, the other producing gamma rays, electromagnetic radiation also travelling at the speed of light, both crossing 130 million light-years of universe and arriving at Earth separated by 1.7 seconds. The 1.7-second gap is not a discrepancy, it is information. The gamma-ray burst is produced slightly after the peak of the merger. The jet takes a little time to form and break out from the merged system, so a small delay between the gravitational wave chirp and the gamma-ray burst is exactly what the models predicted. The fact that the delay was 1.7 seconds rather than days or weeks or years confirms something that general relativity had long predicted, but never directly tested at cosmological distances. Gravitational waves travel at the speed of light. Exactly, not approximately. Within the measurement precision of the detection, they are indistinguishable. Einstein, who had predicted gravitational waves in 1916 while not quite believing they would ever be detectable, would almost certainly have appreciated the neatness of this confirmation. He might also have found it somewhat ironic that it was confirmed by an event he never lived to hear about, detected by an instrument he never imagined, announced at a press conference he was not invited to because he had been dead for 62 years. What followed the detection was the largest coordinated astronomical observation in history. The alert went out, not just to the gamma-ray burst community this time, to everyone. Every observatory with the ability to observe the target region received the coordinates. Optical telescopes, radio telescopes, X-ray observatories, infrared detectors, observatories on every inhabited continent, and in orbit above the atmosphere. The astronomical community, which normally operates with the measured pace of people who know their targets, have been there for billions of years and will continue to be there next month, suddenly found itself in the grip of something very like the urgency that gamma-ray burst astronomers experience routinely. Because the kilonova that was expected to follow the merger would fade, and the information it carried would fade with it, and this particular event might not repeat for a very long time. 70 observatories ultimately contributed to the observation campaign. 7 continents, space and ground, every wavelength. The number of scientists involved in the subsequent papers, published simultaneously across multiple journals a few weeks later, exceeded 4,000. A single event observed by 4,000 scientists with 70 observatories, producing papers with more authors than most scientific collaborations have members. It was, by any reasonable measure, the most observed event in the history of astronomy. What they saw, building over hours and days and weeks, was the kilonova, a glowing fireball of newly synthesized heavy elements, brightening in the infrared and optical, fading across all wavelengths as the material expanded and cooled. The spectra were extraordinary, the fingerprints of elements heavier than iron, assembled in the neutron-rich environment of the merger in the seconds after the collision. The kilonova of GW170817 was, among many other things, a visible demonstration of heavy element synthesis happening in real time, at a distance of 130 million light-years, with 70 observatories watching. What GW170817 confirmed, in a single extraordinary event, reads like a list of everything the field had been trying to establish for decades. Short gamma-ray bursts come from neutron star mergers. Confirmed. The gravitational wave signal identified the progenitor unambiguously, and the gamma-ray burst arrived 1.7 seconds later from the same location. Gravitational waves travel at the speed of light. Confirmed. The 1.7-second delay is fully explained by the physics of jet formation, not by any difference in propagation speed. Neutron star mergers produce kilonovae. Confirmed, the optical and infrared transient was detected, studied, and its spectrum measured. Neutron star mergers are sites of heavy element synthesis. Confirmed, the kilonova spectrum showed the signatures of R process elements, including strontium, definitively identified for the first time in such an event. Multi-messenger astronomy works. Confirmed, emphatically, spectacularly, beyond any reasonable doubt. Each of these confirmations was, individually, a significant scientific result. Together, in a single event on a single August morning, they represent one of the most productive days in the history of astrophysics. The field did not advance incrementally on the 17th of August 2017. It vaulted. There is a quality to this moment, to the convergence of gravitational waves and gamma rays, of dead stars and ancient light, of an instrument sensitive to 1/10,000th of a proton diameter, and a satellite that could pivot in 90 seconds. That feels like something more than the accumulation of good science and good engineering, though it is certainly both of those things. For 100,000 years, we listened to the universe with one ear. On the 14th of September 2015, we opened the other, and on the 17th of August 2017, for the first time, we heard a single event in stereo. The universe had been speaking in two languages all along. We had simply been missing half the conversation. Consider for a moment the gold. Not all gold everywhere. That would be an ambitious scope for a single paragraph. But some specific gold. The gold in a wedding ring, perhaps, if you happen to be wearing one, or in a necklace, or in the microscopic contacts of the phone that may be sitting beside you right now, connecting its circuits with the reliable conductivity that made gold indispensable to electronics long before anyone thought about its decorative applications. Or if none of those are immediately to hand, simply the gold that exists somewhere near you in the world, in a jeweller's window, in a bank vault, in the fillings of a stranger's teeth on the other side of a wall. Where did it come from? Not the mine, not the river. Those are merely where we found it. The question is deeper than that, and the answer is one of the most extraordinary things that has emerged from the study of gamma-ray bursts, a story that begins in the violence of the early universe and ends with a quietness that the violence in no way prepares you for on the finger of someone you love. The periodic table, in its familiar form, organizes the elements by atomic number, the number of protons in the nucleus. Hydrogen is 1, helium is 2, carbon is 6, oxygen is 8, iron is 26, gold is 79, uranium is 92. For the first half of the 20th century, the question of where these elements came from was genuinely open. The universe, shortly after the Big Bang, contained almost exclusively hydrogen and helium, the two simplest elements, produced in the first few minutes of cosmic history when the universe was hot enough and dense enough for protons and neutrons to fuse. Everything heavier than helium had to be made somewhere else, at some later time, by some process that the early universe was not yet capable of. The answer, when it came, was stars. In 1957, a landmark paper by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, known in the field as B2FH, which sounds less like a scientific citation and more like a particularly cryptic password, laid out in systematic detail how nuclear fusion inside stars could account for the production of elements all the way up to iron. The carbon in your body was forged in a stellar core. The oxygen you are breathing was assembled in a star. The calcium in your bones, the phosphorus in your DNA, the iron in your blood, all of it built, element by element, in the nuclear furnaces of stars that lived and died before the sun was born, and scattered their contents into the interstellar medium for the next generation of stellar systems to inherit. This was, and remains, one of the most profound discoveries in the history of science. We are, in the most literal possible sense, made of stardust. The phrase has become so familiar that it risks losing its force. But it is not a metaphor. It is a precise, experimentally confirmed description of where the atoms in your body came from. You are the recycled interior of ancient stars. But B2FH had a problem. Iron is element 26. The periodic table has 92 naturally occurring elements. What about everything from element 27, cobalt, all the way up to element 92, uranium? What about gold at 79? What about platinum at 78? What about all the heavy elements that stellar fusion cannot produce? Because fusing iron and heavier nuclei into still heavier ones requires energy rather than releasing it. Stars burn by releasing energy from fusion. They cannot sustain a process that costs them energy. Once the iron core has accumulated, the fusion chain stops. The elements above iron cannot be made this way. What you need instead is neutrons, specifically a flood of them, an environment so saturated with free neutrons that atomic nuclei can capture them one after another before they have time to decay, building up heavier and heavier isotopes by the rapid addition of neutrons to an existing nucleus. This is called the R process. The R stands for rapid, because the neutron capture has to happen faster than the radioactive decay that would otherwise transform the nucleus into something else before it could absorb the next neutron. It is a process of assembly under extreme pressure of time, nuclei being built in an environment where the neutrons are arriving so quickly that the nucleus has no opportunity to relax into a stable configuration before the next one arrives. The R process was theorized in the same 1957 paper that identified stellar nucleosynthesis. The problem was always the same. Where does it happen? What environment in the universe provides a flood of free neutrons intense enough and dense enough and hot enough to assemble gold from lighter elements in the fraction of a second available before the opportunity passes? For decades, the leading candidate was the supernova, the explosive death of a massive star with its collapsing core and its flood of neutrinos and its extreme temperatures and densities. It was a reasonable hypothesis. Supernovae are certainly extreme enough. They certainly scatter material into the surrounding space, and they certainly produce neutrons in quantity in the collapsing core. The problem was that the models kept not quite working. The neutron flux in a supernova, while impressive, didn't seem to be quite right for the R process. The conditions were close, but not exactly what the physics required. The heavy element abundances predicted by supernova models didn't match the heavy element abundances observed in old stars. The field was left with a process it understood and an environment it couldn't quite identify. The answer, it turned out, had been waiting for us in the collision of two neutron stars. A neutron-star merger is, by definition, the collision of two objects made entirely of neutrons. The material ejected in the merger, the matter that is flung outward in the explosion rather than falling back into the remnant, is extraordinarily neutron-rich. Not merely neutron-rich in the way that a collapsing stellar core is neutron-rich, but neutron-rich in the way that only something literally composed of neutrons can be. The ejector from a neutron-star merger is essentially pure neutron-star material, suddenly liberated from the gravitational prison that was holding it together, expanding rapidly outward and finding itself in an environment where the R process can operate exactly as the physics requires. The temperatures are right, the neutron densities are right, the timescale, milliseconds to seconds, is right. Everything the R process needs is present in the debris of a neutron-star merger, in exactly the quantities and conditions the theory demands. The merger is not merely consistent with being a site of R process nucleosynthesis. It is, in the most literal sense, a factory for it. In the seconds following the merger, as the ejected material expands and cools, heavy nuclei are assembled at a rate and in a variety that no other known environment can match. The R process runs through the periodic table above iron with systematic thoroughness. Strontium, barium, gold, platinum, uranium, and everything in between, built nucleus by nucleus in the expanding fireball of a dead star collision. The kilonova that results is not merely an explosion, it is a synthesis event. It glows in part with the radioactive decay energy of the very elements it is producing. On the 17th of August 2017, astronomers watched this happen. In the aftermath of GW 170817, the neutron-star merger that we arrived at earlier tonight, 70 observatories turned their instruments toward N GC 4993 and recorded the kilonova as it brightened and faded over days and weeks. The spectra they collected were unlike anything previously observed in such an event. Absorption and emission features from heavy elements, the distinctive fingerprints of atoms that can only be assembled in a neutron-rich environment, appeared in the data with a clarity that left very little room for alternative interpretations. Strontium was identified definitively, element 38, present in the kilonova spectrum in quantities that matched R process predictions. The broader pattern of the spectrum was consistent with the lanthanide elements, the group that runs from lanthanum at 57 to lutetium at 71, which are heavy, R process products with optical properties that give kilonova their characteristic infrared glow. The data was, for those who had spent careers arguing that neutron-star mergers were R process sites, deeply satisfying. For the field as a whole, it was confirmation of something that had been theoretically predicted, but never directly observed. The universe making gold, in a detector, in real time. Gold was not individually identified in the GW 170817 spectra. The technical challenges of distinguishing individual heavy elements in the complex, rapidly evolving environment of a kilonova are considerable, and strontium was the clearest identification. But the R process signature was unambiguous, and gold is an R process product. Where the R process ran, gold was made. The spectra were reading the output of the periodic table's upper floors, and gold was on those floors. How much gold does a neutron-star merger produce? The estimates, based on GW 170817 and on theoretical modelling of the R process yields, suggest that a single merger can produce several times the mass of the Earth in gold and platinum alone. Not flecks, not veins. Masses of gold comparable to entire planets, scattered into the surrounding space as the kilonova expands. This gold, this extraordinary quantity of newly synthesized heavy metal, joins the interstellar medium of its host galaxy. It becomes part of the diffuse material between the stars, drifting for millions or billions of years, until it encounters a region of sufficient density to trigger the collapse of a new molecular cloud. A new solar system forms. The heavy elements from ancient mergers are incorporated into the disk of gas and dust from which planets condense. A rocky planet accretes, dense materials sink toward its core during the molten phase, which is why most of the gold in the Earth's interior is inaccessible to us, locked in the core alongside the iron. The gold that we can actually reach, the gold in ore deposits, in river sediments, in the accessible crust, arrived later, delivered by asteroid impacts in the period after the Earth's surface had solidified. The gold in a wedding ring passed through several stages of cosmic history before it arrived on anyone's finger. It was assembled in the collision of two neutron stars. It drifted through interstellar space as part of an expanding nebula. It was incorporated into the disk from which the solar system formed. It settled into the Earth's crust via asteroid impacts billions of years ago. It was mined, refined, shaped by human hands, and exchanged at a moment of significance between people who almost certainly were not thinking about neutron star mergers at the time, because that would be an unusual thing to think about at a wedding, though not, it must be said, an unwelcome one if you happen to find these things interesting. There's a version of this story that could be told as a geology lesson or a chemistry lesson or a nuclear physics lecture, but at its core, at the emotional truth underneath all the nuclear binding energies and R process yields and kilonova spectra, it is a story about connection, about the fact that the most intimate objects in human life are made of material that was forged in the most violent events the universe produces, about the distance in both space and time that separates the collision of two dead stars from the moment a ring is slipped onto a finger. That distance is approximately 10 billion years and several billion light-years, depending on which particular neutron star merger produced which particular atoms. The gold has been travelling for most of the age of the universe to get here. It arrived on your finger, or in your phone, or in a jeweller's window somewhere nearby, via a route that passed through the most violent collision physics can produce. And it sits there now, quietly, doing what gold does, reflecting light, conducting electricity, resisting corrosion with a stubbornness that has made it valuable to human beings since we first discovered it, with no outward indication whatsoever of where it has been. The universe conceals its history well, but it does not conceal it completely. And on the 17th of August 2017, for a few glorious weeks of observation, it showed us its hand. There is a layer of the atmosphere, roughly 15 to 35 kilometers above where you are lying right now, that deserves considerably more appreciation than it typically receives. It is called the ozone layer, and it is thin, genuinely almost implausibly thin. If you compressed all the ozone in the atmosphere down to sea level pressure, it would form a blanket approximately 3 millimeters thick wrapped around the entire planet. 3 millimeters. The thickness of two stacked coins. This is what stands between the surface of the Earth and the full intensity of the sun's ultraviolet radiation, which would, without it, make the sustained existence of complex life on land essentially impossible. The ozone layer is not dramatic. It does not announce itself. It simply sits up there, quietly absorbing ultraviolet photons, converting them to heat, and getting on with the business of making the planet habitable with a modesty entirely disproportionate to its importance. We mention this now because gamma-ray bursts, for all their distance and their violence and their billions of light-years of remove, have a specific and rather pointed relationship with ozone. And understanding that relationship is the key to understanding what it would actually mean, not in the abstract cosmic sense, but in the concrete biological sense, for a gamma-ray burst to affect the Earth. This is not, to be clear from the outset, a chapter about imminent danger. The risk of a gamma-ray burst affecting Earth in any meaningful way within the foreseeable future is extremely small, and we will get to the numbers in due course. This is something quieter and more interesting than a threat assessment. It is a chapter about Earth's place in a dynamic universe, about the ways in which the cosmos and the biosphere have, across 4.5 billion years, been in conversation with each other, whether the biosphere was aware of it or not. When a gamma-ray burst fires its jet toward Earth, the gamma rays themselves do not reach the surface. The atmosphere absorbs them. This is, in fact, why we need satellites to detect them at all. But the absorption is not harmless. When a gamma-ray photon strikes a nitrogen or oxygen molecule in the upper atmosphere, it initiates a cascade of chemical reactions that produces nitrogen oxides, reactive compounds that are, among other things, highly effective at destroying ozone. The chemistry is not simple, but the consequence is straightforward. A sufficiently energetic gamma-ray burst, with its jet directed at Earth, would flood the upper atmosphere with enough energy to trigger the production of nitrogen oxides on a scale that could deplete the ozone layer across the hemisphere facing the burst. Not by a few percent, as the aerosol sprays of the 20th century managed, but potentially by 20, 30, 40% or more. The depletion would not be instantaneous and it would not be permanent. Ozone recovers, given time. But the recovery takes years, possibly decades, and during that recovery period the surface of the Earth would be exposed to levels of ultraviolet radiation that the biosphere has not experienced in a very long time. The consequences of elevated ultraviolet radiation are not mysterious. Ultraviolet damages DNA. It disrupts photosynthesis. It is particularly lethal to the phytoplankton that form the base of marine food chains, the microscopic organisms floating in the surface layers of the ocean that are responsible for roughly half of all oxygen production on Earth, and that support, directly or indirectly, virtually everything else that lives in the sea. If you want to cause a mass extinction without the theatrical flair of an asteroid impact, depleting the phytoplankton is an efficient and thoroughly unpleasant way to go about it. Which brings us, with appropriate epistemic caution, to the late Ordovician. 445 million years ago, the Earth looked nothing like it does today. The continents were arranged differently. The oceans covered regions that are now mountain ranges. Life, which had been diversifying in the seas for hundreds of millions of years, had only recently begun to establish itself on land, tentatively, in the form of primitive plants and the earliest arthropods. Nothing yet that would have looked particularly impressive from a distance. The dominant ecosystems were marine. The shallow seas of the Ordovician teemed with trilobites and brachiopods, and the ancestors of every major animal group that would eventually inherit the planet. Then something happened. In a geologically brief period, perhaps 1 million years, perhaps less, roughly 85% of all marine species disappeared. The Ordovician Silurian extinction event is the second largest mass extinction in the history of animal life on Earth, exceeded only by the end Permian event 250 million years later that wiped out perhaps 96% of all species and came uncomfortably close to ending the animal experiment entirely. The cause of the Ordovician extinction has been debated for decades. The leading hypothesis involves a period of intense glaciation, the growth of enormous ice sheets over the southern supercontinent Gondwana, which lowered sea levels, cooled the oceans, and disrupted the shallow marine environments where most complex life was concentrated. The glaciation hypothesis is well supported by geological evidence, but it raises a question that the evidence is less clear about. What triggered the glaciation? In 2004, the astrophysicists Adrian Melott and Brian Thomas published a paper proposing a provocative possibility, a gamma-ray burst within a few thousand light-years of Earth, aimed by the lottery of celestial geometry in our direction, could have depleted the ozone layer severely enough to cause exactly the pattern of extinction observed at the end of the Ordovician, the initial die-off of surface-dwelling marine organisms and phytoplankton, followed by a collapse of food chains, followed by the broader extinction that the geological record documents. The glaciation in this scenario might have been a consequence rather than a cause. The death of vast quantities of phytoplankton would have reduced atmospheric carbon dioxide. Phytoplankton absorbs CO2 as part of photosynthesis, and when they die in enormous numbers, that absorption stops while the decomposition of their bodies releases other compounds that affect atmospheric chemistry. A sufficiently large disruption to the carbon cycle could, in principle, trigger a cooling event. The ice sheets follow the ozone depletion. The cause is a beam of gamma rays from a dying star, arriving without warning from somewhere in what is now the constellation Cygnus or Sagittarius, hitting the planet that 445 million years later would be occupied by creatures capable of working out what had happened. It is, to be entirely clear, a hypothesis, not a confirmed cause. The geological record from 445 million years ago is incomplete in ways that make definitive attribution difficult. There is no gamma-ray burst smoking gun preserved in the rock strata, no iridium layer, as there is for the asteroid impact at the end of the Cretaceous, no clear geochemical signature that points unambiguously to an extraterrestrial energy source. What the record shows is consistent with a gamma-ray burst having contributed. It is also consistent with other explanations. The sleepy investigator, if it covered mass extinctions, would describe the evidence as intriguing but circumstantial, exactly the kind of mystery that rewards further investigation without yet rewarding confident conclusions. So, how worried should we actually be? The answer, satisfyingly, is not very, and the reasoning is worth following carefully because it illuminates something genuinely interesting about Earth's position in the galaxy. A gamma-ray burst capable of causing significant ozone depletion at Earth would need to satisfy two conditions simultaneously. It would need to be close enough that the fluence, the total energy arriving at Earth, exceeds a threshold sufficient to drive the relevant atmospheric chemistry, and it would need to be pointed at us, with its jet directed along the line between the source and Earth. Both conditions are required. A nearby burst pointed elsewhere is harmless. A distant burst pointed at us is too dilute to matter. The closeness requirement is roughly within about 6,000 light-years, depending on the burst's intrinsic energy. The Milky Way is 100,000 light-years across. 6,000 light-years is a meaningful fraction of the galaxy, but it excludes the most prolific gamma-ray burst environments, the dense, actively star-forming regions near the galactic center, which are both more likely to produce bursts and further away than 6,000 light-years from us. The pointing requirement reduces the probability further. A gamma-ray burst jet covers only a small fraction of the full sky, perhaps 1% or 2%. The probability that any given burst is aimed at Earth is correspondingly small. Combining these factors, the best current estimates suggest that a potentially hazardous gamma-ray burst within the relevant distance and aimed at Earth occurs roughly once every few 100 million years on average. Over the 4.5 billion year history of the Earth, that implies perhaps 10 to 15 potentially hazardous events in total, a number consistent with the handful of major mass extinctions the geological record documents, though the match between these numbers and the extinction record is suggestive rather than conclusive. Correlation, as the scientists are always reminding us, is not causation. Sometimes it just looks like it. There's a broader context to this calculation that is worth stepping back to appreciate. The Sun sits roughly 26,000 light-years from the galactic centre, in a relatively quiet region of one of the Milky Way's spiral arms. The stellar density here is moderate, not the crowded, explosive environment of the inner galaxy. With its higher rate of massive star formation, its more frequent supernovae, its greater concentration of everything that produces gamma-ray bursts, but not the sparse, metal-poor outer reaches of the galaxy either, where the heavy elements needed to build rocky planets are in short supply. We are, in other words, in what has been called the galactic habitable zone, a band of galactic real estate where the conditions for complex life are reasonably favourable, not too close to the galactic centre, where the radiation environment is hostile and the burst rate is high, not too far out, where the chemistry for rocky planets is inadequate, somewhere in between, where a planet can form with the right elements and then be left in relative peace for long enough to develop something interesting. The fact that we are here, having this particular conversation about gamma-ray bursts, is in part a function of where we are in the galaxy. A civilization that had evolved on a planet in the inner galaxy would face a considerably higher rate of potentially hazardous events, and might, for that reason, not have had the 4 billion years of relative stability that complex life seems to require. Our cosmic address, it turns out, is not incidental to our existence. It was chosen for us by the lottery of stellar formation, and it happens to be a good one. Return, then, to the ozone layer. That 3-millimeter blanket of improbably thin gas sitting quietly above the clouds, absorbing ultraviolet photons with patient diligence. It has been doing this, in one form or another, for hundreds of millions of years. It has survived whatever the universe has thrown at it, the solar flares, the ice ages, the asteroid impacts, and possibly, if Melot and Thomas are right, at least one gamma-ray burst arriving from the depths of the Milky Way. It has been, on each occasion, sufficient, the ozone depleted and recovered, life, which had survived the initial disruption, diversified into the ecological spaces left by whatever had been lost. The planet continued. 445 million years after the worst extinction event it had survived to that point, it produced creatures who would build satellites to watch for gamma-ray bursts, write papers hypothesizing about their connection to ancient extinctions, and eventually lie in the dark listening to someone describe all of this in a calm voice at a reasonable pace. The thin blue line held. It is holding now, above you, as it has held through everything the universe has managed so far. That is not nothing. That is quietly everything. A photon leaves a star. This is not in itself remarkable. Stars produce photons in quantities that make any human attempt at large numbers feel slightly embarrassed. Every second, the Sun alone releases approximately 10 to the power of 45 photons, a number so far beyond the reach of intuition that the only honest response is to simply accept it and move on. Stars make light. That is, in a very fundamental sense, what stars are for. But this particular photon is leaving a particular star at a particular moment in the history of the universe, and both the star and the moment are extraordinary. The star is one of the first, not the very first. Astronomers are careful about superlatives when the evidence is still accumulating, but among the earliest stellar objects that the universe produced, formed from the primordial hydrogen and helium of the Big Bang, before the interstellar medium had been enriched by even a single generation of stellar deaths. These first stars, which cosmologists call population 3 stars, are theoretical objects we have not yet directly observed, but whose existence the physics of the early universe requires. They were massive, perhaps hundreds of times the mass of our Sun, and they burned with extraordinary intensity, living their brief, brilliant lives in millions of years rather than billions, and dying in explosions that seeded the surrounding space with the first heavy elements the universe had ever produced. This star is dying now, in the way that the most massive stars die, catastrophically, completely, with a gamma-ray burst that fires 2 jets of energy outward along its rotation axis at close to the speed of light. The burst lasts perhaps 30 seconds. The jets carry the energy of 10 billion years of solar output. The photons race outward in all directions from the source, the gamma rays leading the way, the afterglow following behind them as the jets drive their shockwave into the surrounding gas. One particular photon, one among the unimaginable multitude produced in the first seconds of the afterglow, happens to be travelling in a specific direction, toward a region of space that is, at this moment, empty, toward a place where nothing yet exists and where nothing will exist for a very long time. It begins its journey. The universe at this moment is approximately 600 million years old. It does not look like the universe you would recognize. It is smaller. Space has been expanding since the Big Bang, and the distances between things were considerably less than they are now, though the universe was already vast beyond any useful comprehension. It is warmer. The cosmic microwave background radiation, the afterglow of the Big Bang itself, still fills all of space with a faint warmth that will take billions more years of expansion to cool to the chill it maintains today. And it is, in the grandest structural sense, still finding itself, the great web of filaments and voids and galaxy clusters that defines the large-scale architecture of the modern universe, is just beginning to assemble, gravity slowly drawing matter together into the sheets and nodes of what cosmologists call the cosmic web. There are galaxies, not the grand, settled spirals of the mature universe, with their orderly arms and their ancient stellar populations, and their supermassive black holes sitting patiently at the centre. The galaxies of 600 million years after the Big Bang are small, irregular, intensely active, churning through their gas at rates that will produce all the heavy elements the later universe will inherit, dying young and bright and prolifically, seeding the cosmos with the raw materials of everything that will follow. The photon travels through this universe. It passes through gas clouds and the halos of infant galaxies. It carries, encoded in its wavelength and polarization, information about everything it encounters along the way. Every cloud of hydrogen it passes through leaves a faint imprint on its spectrum, a record of the chemistry of the early universe that astronomers, billions of years later, will be able to read like a message written in absorption lines. The photon does not know this. Photons are not, in general, aware of their archival significance. 1 billion years pass. The universe has cooled slightly. The cosmic web has become more defined. Galaxy clusters are forming at the intersections of vast filaments of matter, stretching across hundreds of millions of light years. In one unremarkable region of one unremarkable filament, a particular concentration of gas is beginning to collapse. Slowly, under its own gravity, the way all molecular clouds eventually collapse when they have accumulated enough mass and lost enough of the thermal energy that was keeping them puffed up and diffuse. The photon passes through this region on its way through the expanding universe. The cloud does not yet know what it will become. The photon does not pause to observe. It simply travels at the speed of light through a universe that is gradually, generation by generation, becoming more complex. 4 billion years after the photon began its journey, 4 billion years, longer than the Earth will eventually live, a star ignites in a region of the universe that the photon passed through perhaps 3 billion years earlier. It is an ordinary star, yellow, middle-aged in its prospects, orbited by a disk of gas and dust that will, over the next 100 million years, assemble itself into a system of planets. The star is not the first in its neighbourhood, nor will it be the last. It is simply a star, one of several 100 billion in the galaxy that contains it, one of perhaps 2 trillion galaxies in the observable universe, a perfectly ordinary stellar object going about the perfectly ordinary business of converting hydrogen into helium and light. The photon, which has now been travelling for 4 billion years and has covered a distance that no unit of human measurement was originally designed to accommodate, is still moving. It has not slowed. It has not faded. It has stretched, its wavelength pulled longer by the expansion of the universe, shifting from the gamma rays of its birth through X-ray energies and eventually into the optical range and beyond. But it carries its information intact, encoded in the correlations between its properties and the properties of everything it has passed through. It continues. 9 billion years after the photon left its dying star, 9 billion years, more than twice the current age of the Earth, something remarkable happens on the third planet of that unremarkable yellow star. In the shallow seas of a world that is warm and wet and covered almost entirely by ocean, in a thin chemical broth lit by filtered sunlight, something begins to replicate, imperfectly at first, then with increasing fidelity, then with increasing complexity, as the copies that replicate most reliably outcompete the copies that don't, and the process that will eventually be called natural selection begins its patient, undirected work of building complexity from chemistry. The photon does not know this either. It continues through the expanding universe, carrying its ancient light, indifferent to the biology unfolding on a small planet that it will not reach for another 4 billion years. 13 billion years after the photon began its journey, give or take a few 100 million years, which is the kind of imprecision that becomes acceptable when the numbers are this large, the universe looks very different from the one the photon left behind. As the cosmic web is fully formed, galaxy clusters anchor the great filaments, the Milky Way is a mature spiral galaxy, its 100 billion stars arranged in elegant arms around a central bulge, a supermassive black hole sleeping quietly at its heart. The third planet of the yellow star, Earth as the creatures now living on it have named it, which is a charmingly provincial name for a planet but does at least have the virtue of simplicity, has been inhabited by complex life for over 500 million years. Those creatures have, in the last century or so of their existence, developed a series of increasingly sophisticated ways of studying the universe. They have built telescopes and observatories and eventually satellites. Instruments launched above the atmosphere that can detect the kinds of radiation that the atmosphere helpfully absorbs before it can cause any inconvenience to the biology below. They have built detectors sensitive enough to catch individual photons that have been travelling for billions of years. Among those detectors is one that is, on this particular day, pointed in exactly the right direction. The photon strikes the detector. In the language of semiconductor physics, this produces a photoelectron, a single electron liberated from the detector material by the energy of the photon, setting off a cascade of electronic signals that propagate through the instrument's circuits at the speed of electricity, which is fast enough for our purposes, Numbers change in onboard computers. Data is formatted and transmitted to a ground station. The ground station forwards the data to scientists at universities and research institutes on several continents, who will spend the next weeks and months analysing what it contains. The photon's journey, which began in the death of a star 600 million years after the Big Bang, ends in a detector on a satellite orbiting a planet that did not exist when the journey started. The star that produced it is gone. The galaxy that hosted it has merged with others and been reshaped by 1 billion years of cosmic evolution into something its original stars would not recognize. The universe through which the photon travelled is more than twice as old as when it set out. And somewhere an astronomer's phone goes off. What that photon and the afterglow it was part of tells us when we analyse its spectrum is extraordinary. The afterglow of a distant gamma-ray burst is a flashlight. As it travels through the universe, it passes through every cloud of gas between the source and us, and each cloud imprints its chemical signature on the spectrum of the light, absorbing specific wavelengths that correspond to specific elements and ionization states, leaving a record of the chemistry of the universe at every point along the line of sight. The further away the burst, the more cosmic history is encoded in that spectrum. The most distant bursts from the era of the first stars carry information about the universe at an age of a few 100 million years, a period that is otherwise almost completely inaccessible to observation. We cannot yet see the first stars directly. They are too distant, too faint, their light too thoroughly shifted to infrared wavelengths by the expansion of the universe for even our most powerful telescopes to detect individually. But the gamma-ray bursts they produce, which are for those brief seconds the brightest events in the universe, bright enough to be detected from anywhere in the observable cosmos, act as beacons in the darkness, and the spectra of their afterglows carry the fingerprints of the gas those photons pass through on their way to us. From those fingerprints, we can read the chemical state of the universe at the epoch of reionization, the period between roughly 100 million and 1 billion years after the Big Bang, when the first stars and galaxies ionized the neutral hydrogen that had filled the cosmos since recombination, transforming the universe from opaque to transparent. This transition reshaped everything. It is the moment when the universe, in a very real sense, turned the lights on, and the gamma-ray bursts from that era are the best probes we have of what it looked like when they did. The most distant confirmed gamma-ray burst detected so far occurred when the universe was approximately 630 million years old. The photons from its afterglow had been travelling for over 13 billion years before they arrived at our detectors. No other individual event has been observed at greater distance. No star, no galaxy, no quasar has been directly pinpointed at a larger redshift. Gamma-ray bursts are, in this precise sense, the most distant things we have ever seen. They are also, through the irony that the universe seems to specialize in, among the youngest things we have ever seen, snapshots of the cosmos in its early chapters, when the elements were still sparse, the galaxies still forming, the great structures of the cosmic web still assembling themselves from the primordial fluctuations of the Big Bang. When we observe the afterglow of a burst from 13 billion years ago, we are not looking at the ancient past of a universe that has changed beyond recognition. We are looking at the universe's childhood, preserved in light that has been travelling toward us since before the Earth existed, arriving at our instruments with the patience of something that has simply been going in one direction for a very long time and has finally arrived. A star died 13 billion years ago, give or take, in a galaxy we cannot name, In a region of the universe that looked nothing like our neighborhood looks today, a massive star ran out of fuel and collapsed and fired its jets into the cosmos and produced a flash of gamma rays that raced outward in all directions. One of those directions was here. The photons had been on their way ever since, through the formation of the Milky Way, through the birth of the Sun, through the long, patient unfolding of life on Earth, through all of human history from the first fire to the last satellite launch. They have been travelling at the speed of light, carrying their ancient information through a universe that has been expanding around them the entire time. They arrived, they struck a detector, a number changed, an alert fired, and in a control room somewhere, or on a phone in a pocket, or on a screen in an office at a university at 3 in the afternoon or 3 in the morning, a scientist saw the notification and understood, in the way that scientists understand things, precisely, carefully, with full awareness of the uncertainties involved, that the universe had just sent a message from its own beginning. The universe does not require us to be watching. It sends its light regardless. But it is a particular quality of this moment in cosmic history that something is here to receive it, something that can build the instruments, write the software, do the mathematics, and sit quietly in the dark afterward, turning the numbers over, trying to understand what 13 billion years of travel has to say about where everything came from. We're very new here. The light is very old, and it found us anyway. Right now, somewhere in the observable universe, a star is dying in exactly the way we've been describing. Not metaphorically, not as a thought experiment. The universe produces roughly 1 detectable gamma ray burst per day, which means that statistically, while you have been lying here listening to all of this, at least one has occurred. A star has collapsed, or 2 neutron stars have completed their billion-year spiral and touched, and the result, a flash of gamma rays carrying the energy of 10 billion years of solar output, is racing outward in its narrow beam, crossing whatever distance separates it from us, aimed at wherever it happens to be aimed. Most of those beams miss us, almost all of them in fact. The universe is generous with its violence and careless with its aim, but somewhere out there, 1 or 2 of tonight's bursts are travelling in our general direction. They will arrive in years, or centuries, or millennia, or millions of years, depending on how far away they happen to occur. Swift will catch them, or whatever Swift's successor turns out to be, or whatever instruments humanity has built by the time the photons arrive. And someone's phone will go off, and someone will look at the coordinates, and the data will be collected before the afterglow fades. The universe keeps announcing itself. We keep building better ears. There is something quietly remarkable about the position we occupy in this story. We are not the central characters. We are not even significant extras. We are a thin smear of biology on a mid-sized rock, orbiting an ordinary star, sitting in a quiet neighborhood of an unremarkable galaxy, watching events so distant and so energetic that the light from them has been travelling since before the Earth existed. We did not cause any of this. We barely qualify as witnesses, given how recently we arrived and how narrowly our instruments catch the signals. And yet here we are, having worked it out. The Vela satellites and their accidental discovery, the decades of empty error boxes and frustrating near misses, Beposax and its Italian-Dutch persistence, Swift, rotating in 90 seconds, the LIGO chirp rising and falling in less than a second, the strontium lines in a kilonova spectrum 130 million light-years away, the ancient afterglow of a burst from 600 million years after the Big Bang, carrying its message through the full span of cosmic history to arrive in a detector we built last Tuesday. The universe concealed all of this extremely well, For an extremely long time, we found it anyway. If these quiet journeys through deep space and deep time bring you something, a little stillness, a place to let the mind drift while the night grows late, the sleepy astronomer will be here for the next one. For those whose curiosity turns downward rather than up, toward the drift of continents, the long biography of rivers, the patience of stone, the sleepy geographer is waiting. And for those drawn to darker, quieter mysteries that are rather more human in origin, the sleepy investigator has something for you as well. If tonight's episode found its way to you through a recommendation or a review, or someone who thought you might be the kind of person who lies awake thinking about neutron stars, please pass it on. It costs nothing. It means rather a lot. The gold in whatever you are wearing right now has been waiting 13 billion years to be here. The ozone layer is holding. The nearest gamma-ray burst is pointed elsewhere. This is the sleepy astronomer, wishing you clear skies and peaceful dreams. Good night, and sleep well beneath gentle starlight.